Yes.
To share your screen, you know, with your presentation. To check if it works. It should work. It was okay.
Yes. Now I try to up. Do you see it?
Yes, I see it. No problem.
Okay, perfect. It looks like everything. Yeah. Great.
So you have many co-authors, and some of them I don't know.
Yeah.
Of course, I know Francois Julien, and I know Jaël and Marie, no problem. But
Yeah. So this
not...
guy Subrata Das, he works on the synthesis of nanophosphorus. He works in India. So for white LEDs, he provides us the nanophosphorus. And Stéphane Vision.
Naël, I know, yeah.
Yeah, sure. She is in C2N. And Stéphane Vision and Benjamin Damilano, they are in CREA, Centre en Research on Nitrites in Nice. And they are doing these porous structures that I will present at the end.
Okay.
So these are mainly nitrite people, except phosphorus people.
And who is the first author?
So this is my PhD student who is supposed to defend very soon, but we are still on the manuscript.
I see. Okay, I think it's almost time, so I can actually start the second session of the day. So we have 3 more invited talks according to the schedule for today, and this session is started with Maria Chernyshova, also from C2N, with a talk entitled Nitrite Nanostructures for Light Emitting Dyes.
Thank you very much, Vladimir. Thank you for the invitation and for your kind introduction. So I will present this work on different types of nanostructures in nitrites, all of them for light emission. So this work is a collaboration of many co-authors, but the main part is done in our lab, Center of Nanoscience and Nanotechnologies, same as Frank. So here you see our nice new building with big clean rooms, and now almost everything is operational and we are working normally as before getting to this new building. So here is the outline. I will first introduce the issues that we have with thin film conventional nitride LEDs. Then I will present nanowires as a way to improve the performance of the LEDs. I will move to flexible devices based on these nanowires, briefly introduce other applications, not only for the light emission, but also for photo detection or piezo generation. And in the last part, if I have time, I would like to introduce alternative structures, which are not in the form of wires, but in the form of porous films, and how these films can also improve the performance of the light emitting diodes. So let's first take a look on these nitride LEDs. So you know that nitrides are wide bandgap semiconductors. So there was a lot of research to produce LED based on these materials because we can emit blue light. And blue light is essential if we want to do white emission, because we can use part of this blue light down convert with the yellow phosphorus, and with this obtain this nice, highly efficient white LED. So the discovery of these, the way how to do LEDs based on nitrides was awarded a Nobel Prize in 2014 to these 3 Japanese guys, Akasaki, Amano, and Nakamura. And indeed, this was a very important discovery because with the LED, you can reach 300 lumen per watt efficiency, while if you use standard incandescent lamps, you are only around 10 to 20. So there is a huge saving of energy in lighting thanks to these devices. However, these devices are not perfect, and still there are many issues related to inherent material properties, or to material defects. So here you have a list of them. First, what we call green gap. If we try to increase the wavelength of the LED based on InGaN, we have a drop of efficiency because the material properties degrade and we have a lot of internal field. So that's why there is a very big challenge to produce efficient emitters close to 550 nanometers in the green. Then second problem, so-called efficiency droop. If you want to obtain high efficiency, high brightness from your LED, you start to drive it at high current, but unfortunately the efficiency goes down because you start to enter in the regime where many body effects, such as Auger effects, become very important, and you get non-radiative recombination by Auger mechanism instead of producing photons. You also need to work on your material to extract efficiently light, otherwise it is trapped by the internal reflection. You have some feature which is specific to nitrides, which is the internal electric field, because these materials are polar and piezoelectric, so the potential of your quantum well is disturbed, and this internal field reduces the overlap of the wave functions and therefore reduces the efficiency. But I would say the main problem is the problem of the material quality, because nitrides are usually grown on substrates such as sapphire, sometimes silicon carbide. But in all these cases, we're dealing with heteroepitaxy, so we have lattice mismatch between the substrate and the material. And when we introduce quantum wells, we also introduce lattice mismatch. So as a result, we have a lot of threading dislocations starting at the substrate or in the heterostructure itself. And these dislocations degrade the material quality and the radiative efficiency. So with all these issues present in conventional thin film devices, the researchers started to look on alternatives, how we can use other forms of material, for example, nanowires, to try to solve these problems and improve the performance of the LEDs. So let's look on nanowires. So nanowires in nitrides are often not as nano as we may think from the name, because we call nanowires everything which has a diameter close or below to 1 micron, but a length which is much larger than a diameter. Whatever is the definition, these nano objects have a very large surface area and they have a small footprint. This means that you can relax strain by the free surface, which is very important in these materials to avoid dislocations. So on the bottom, you have different examples of nitride nanowires. So nanowires grown by molecular beam epitaxy, which are very small. Then also MBE grown nanowires, but using a mask so that we can order them in this nice hexagonal lattice. And the last example is the growth by MOBPE, where the nanowires are quite big, but nevertheless, we can obtain these homogeneous, nice nitride crystals. So the interest, as I said, is this strain relaxation, because when you have a lattice mismatch with a substrate, you can, in fact, deform the free sidewalls of the nanowire without forming a threading defect. So if we are dealing with thick nanowires and if a dislocation is formed, it can be easily bent to join the lateral surface. So the main volume of the crystal is defect-free. So it means that we can grow these nanowires on different types of substrate, importantly on silicon, but also on other non-conventional substrates like metals, non-crystalline substrates like silicon oxide. And these last days, also people are interested on growing them on 2D materials like graphene. So we have a variety of choice. And we also have new opportunities because we have other degrees of freedom. For example, we can build core shell structures or edge heterostructures. And there is also a possibility of controlling the composition by the local environment. Like in this example from Kishino group in Tokyo, where they just changed the pattern of the substrate, and in the same growth run, they changed the indium incorporation from producing blue emission to producing orange emission. So we apply these nanostructures to LEDs. We can build these defect-free nanocrystals on low-cost substrates. Now for the device, we need a p-n junction for injecting electrons and holes. So we can build this p-n junction either in the axial direction, as we do in conventional thin film devices. And in this case, we can benefit from the strain relaxation in the active region between the indium gallium nitride quantum disks and gallium nitride quantum barriers. And in this case, we can cover the green gap because it's more easy to incorporate indium-rich material without degrading the properties of material. We have also another possibility. We can use the radial dimension and form this p-n junction on the side walls of the nanowires. And in this case, the active area will be the cylinder. So for the same footprint of the device, we can significantly increase the total active area, which means that we will reduce the droop, because for the same current, the current density will be lower, so the droop phenomena or J recombination will be pushed away. And we also can benefit from these vertical sidewalls, which are non-polar M-planes, and we do not have any electric field there, so the radiative efficiency will be higher. So here you have a practical example of a LED grown by MOCVD using silicon nitride mask on a gallium nitride on sapphire template. So first, their core is synthesized, which is n-doped, which will be used for the electron injection. Then the growth is switched to the radial mode, and then the quantum well is deposited, and finally the p gallium nitride shell for the hole injection. So now with these nanowires, we can produce the LED by depositing a transparent contact on the p shells. So what was done here on this example? In this case, we obtain the conventional device with a rectifying IV diodic curve, opening voltage around 3 volts, typical for these LEDs. This device was targeted to emit a blue wavelength around 420 nanometers, and indeed we see this on the electroluminescent spectrum. So here everything is working as expected. However, if we look closer on the shape of this electroluminescent spectrum, we observe that something happens at the long wavelength range. And indeed, if we analyze in more details the behavior of the emission with the injected current, so you see here spectra for increasing injection, we see that first the device starts working almost in the green, and then when we push the current up, we have the blue emission which appears and which becomes dominant. So these reflect some internal inhomogeneities in the wires that we will analyze in the next slides. And we also have another problem. If we look under the microscope on the emission of this nanowire LED, we observe that the intensity from wire to wire is strongly inhomogeneous. So here you see an example of a bad sample where this inhomogeneity is extreme. However, even for state-of-the-art LEDs, this problem exists, which is less visible, but still it's very difficult to achieve perfect intensity homogeneity between different wires. So we will also analyze where this problem comes from and how can we solve it. So first, let's look on the internal inhomogeneity of the nanowires. So here you see the top view cathode luminescence maps. So you see the nicely arranged nanowires, and then maps filtered for the blue emission and for the green emission. So you see that both colors are present in all nanowires. So it's not something which arises from wire-to-wire fluctuation, but it's internal inhomogeneity. And we can also perform cross-sectional CL mapping and analyze in more details where these different wavelengths come from. So we see that, so here you see color filtered map for different wavelengths. So blue emission is on the sidewalls, spread almost over the entire M-plane facets. And when we move to the long wavelength part, we see that this emission is localized close to the top of the wire, where we have the change between the M planes and the semipolar planes in these structures. So we evidence here the presence of intra-wire composition inhomogeneities, and these inhomogeneities can indeed be proved by structural analysis. So on this slide, you see a fiblamella prepared by cutting, lifting out these thin slices of these nanowires. So you see quantum wells on the M planes, and we can perform compositional analysis by EDX mapping. And we have observed from this analysis that there is a gradient of the composition, and on the top part, there was an accumulation of a higher amount of indium, which was responsible for this green emission at the top, where we change from the M plane to the semipolar plane. So we understand that this complex spectral behavior of the electroluminescence comes from the inherent inhomogeneities of incorporation in the growth process. So now, if we want to remove this undesired green emission from the top, we can do it by post-growth processing. So we can basically etch away the contact from the top of the nanowire. So we inject less carriers in this region that we do not want. Or we can even etch away the gallium nitride top part of the wire and remove also this indium-rich part in the quantum well. You see indeed these modifications on the electroluminescence spectrum on the bottom. So you have first the black spectrum where we have the two emissions present. Then when we remove the contact, we privilege the blue emission and we reduce the green one. And if we do ICP etching to remove away material, we have only blue, but we lose intensity because we induce some damage by the ICP etching. So the conclusion here that we indeed can control the color of these LEDs. However, we are losing some part of the active area. So it would be better to control the homogeneity by the growth. However, it's indeed very challenging in these 3D structures where we have different planes present. And now the second problem that I have announced at the beginning is the inhomogeneity of the electroluminescence. So here you see an illustration, SEM top view image of the nanowires, cathodoluminescence map filtered for the quantum well, and the electroluminescence map. So what you observe here is that the cathodoluminescence, that is when we inject carriers in the quantum well by the electron beam, is nicely homogeneous from wire to wire. We have no major faults, so all wires produce more or less same intensity with minor fluctuations. However, when we try to inject carriers by electric injection from the P and N contacts, we have a big issue because we have some wires with a strong signal and other wires which do not produce any signal at all. So we believe from this experiment that this inhomogeneity has nothing to do with structural defects in the quantum wells, but is related to the electrical inhomogeneities of injection. So some problems of the contacts or of the internal structure. So to better understand this, we have analyzed in more detail the internal electrical structure of the nanowires. So what you see on these images is an SEM image of a cleaved wire. So you can see the core, which has a darker color. Then the shell is on the outside, the light gray, and the underlayer. So quantum wells are somewhere between this light gray and this darker gray part. And on the right, you see the corresponding electrical image. So it is electrical beam induced current map, where we just scan the area with the electron beam, and for each position of the beam, we record the induced current. So as you can see, we have a signal between the core grown in the axial direction and the structure grown in the radial direction. It's not what we expect, because in this p-n junction, the signal should be close to the p core where the junction is. And here we have some parasitic electrical activity at the nanowire core where it should be no signal because it's heavily n-doped and there is no junction. And the same thing can be observed if the wire is cleaved perpendicular to the axis. And again, we can find this parasitic electrical signal at the place where we should have nothing. So the hypothesis that we are doing here is that when we are growing these wires, with a high doping level, we form at the surface some discontinuous silicon nitride layer because we send a lot of silane, and this silane can react with nitrogen and form this spontaneous layer. And in some microscopy studies, it has been evidenced. And so this layer can act as traps for carriers. And that's why we have a kind of barrier which prevents us from homogeneously inject carriers in the LED. So if this hypothesis is true, we can in fact solve the problem by changing our contact pattern. Instead of injecting the electrons through the core, as we did before, we can directly inject them in this laterally grown gallium nitride layer. So for that, we have developed processing in several steps. So we deposit both the material contact. I will not detail all the steps, but as a result, we have the possibility to inject holes in the P shell and inject electrons directly in this radially grown gallium nitride N layer. And you can see here a comparison between a standard LED, where we inject the electrons through the core, and this modified design, where we inject them directly in this N underlayer grown radially. You see that if in the first case, we have only 19% of nanowires producing electroluminescence, in the modified design of the contact, we can have 65%. So this is exactly the same sample, just cleaved in two pieces and processed differently. So this means that even if we have these problems of some electrical inhomogeneous inside the structure, by designing the contact, we can solve it. However, of course, for the real devices, we would love to have something homogeneous from the very beginning. So during the growth step, we should be very careful with the doping and with any other parasitic growth on the side walls, which can create barrier for the carrier injection. So if we try to summarize some status of these nanowire LEDs, in fact, there have been a lot of work the last 10 years. So people try to optimize different colors of the LEDs and also to reach white emission. However, today the performance, the quantum efficiency of these devices is still not as good as 2D films. So the problems are this spatial inhomogeneity of the indium incorporation and also some electrical inhomogeneities that may arise during the growth with different doping levels. So the technology is very promising, but it's difficult to compete with the mainstream 2D approach. So for this, maybe it's interesting, instead of trying to do a competition with standard commercial thin film LEDs, we can look for other alternative applications. And today there are a lot of research on two applications. One is the use of micro LEDs for doing micro displays. And the other one that we are concerned with is the development of flexible light sources. So now I will focus on this specific application of nanowires to do flexible LEDs. So we want to develop flexible light sources for different applications today. So for example, this wearable watch or some rollable displays, smartphones that we can bend. We also may want them for lighting, which can be conformally deformed and placed on some complex objects. We also have specific applications for the blue light in flexible, for medical implants, for cochlear hearing stimulating, and also in optogenetics for experiments on animals, where we need to have these flexible light sources to be able to inject them directly in the right position in the brain of this experimental model. So today, the flexible devices are mainly based on organic materials. Indeed, there is a huge market of organic LEDs for displays and for other applications. And these organic LEDs are very advantageous from the cost viewpoint because they are processed at low temperature and on a large scale. And the design is rather flexible, so you can tune the wavelengths by changing the active molecule, which is quite easy. And you also do not have these epitaxial constraints as you have in 3-5 semiconductors. So this gives you more freedom on the material engineering. However, in the organic devices, you can have problems. Well, the first one is that the luminance compared to inorganic LEDs remains low. You cannot drive them at a very high current. And you also have a stability which is worse than in the case of inorganic nitride semiconductors. It's both for electronic properties and for optical properties. So if you compare the performance of OLEDs and indium gallium nitride LED in the blue region, you have 2 orders of magnitude difference on the luminance and also on the lifetime. So indeed, it's very advantageous to use some polymer material, but make it passive and add to this material active inorganic semiconductor, which will produce high brightness and stable in time light. So to do this, there are different approaches today. So one is the use of microstructuring of conventional thin films. Then these films are lifted off from the substrate and transfer printed on a flexible carrier. So this is something which is well developed today, and many industrial groups are pushing this approach. However, here we have all the issues of thin film LEDs with us, and we have also additional issues for these processing steps, for the laser liftoff, printing, doing it in a scalable way, etc. So there are also other alternative approaches. I want to cite these colloidal quantum dot LEDs, because this is a kind of intermediate step between organic devices and inorganic devices. So they typically have organic layers for the carrier injection, and inside they have this quantum dot monolayer where the emission takes place. However, these devices can have very nice colors and are used in displays, but they also have complex electrical injection, and the lifetime of these injecting layers can be short because it suffers the same degradation as in organic devices. So we are analyzing alternative intermediate approach where we use nanowires with contacts to these nanowires, and they are just embedded in a passive polymer membrane, which is used only as a mechanical support. So the idea is that here we combine these 3,5 nanowires, which have a nice lifetime and have a nice brightness. And we combine them with polymers, which are flexible, transparent, and they just act here as a passive support. This means that we can also think about combining membranes with different materials. And like this, we can reach the modularity, which is not within the reach for epitaxial growth in a monolithic approach. So for this approach of transferring nanowires, there have been many studies starting from the early 2011. So the first publication is here from a Korean group. They used a sacrificial underlayer below the nanowires, which is etched, and then the membrane can be easily released and transferred to a different substrate. So in our case, we decided to avoid this under-etching of a sacrificial layer, and we just use a mechanical peel-off by taking advantage of the high aspect ratio of the nanowires. So mechanically, if the nanocrystal has an aspect ratio above 10, it can be easily just broken by trying to separate this membrane from the substrate, and it is broken at the base. So like this, we can peel off membranes over quite a big surface and process them as LEDs. So the processing uses these big nanowires grown by MOVP, by our collaborators in Grenoble. And we use different procedures to develop these LEDs. So first we embed them in PDMS, we peel off, we flip this membrane on a carrier to deposit the back contact. Then we flip again, mount them with some conductive epoxy or some silver paint or whatever, something conductive, and we deposit the top contact, which we have optimized, and the best trade-off was obtained with silver nanowire networks. We can also produce a fully transparent LED with this approach, And in this case, we deposit silver nanowires on the back side and also on the front side. So just a small example of the membrane. This is an SEM image after peel-off, and you see inside the nanowires, they are not broken. So this membrane is now deposited on a carrier, and we need to contact them. So for the contact, we have tried different materials. And as I said, the best for us was the deposition of a silver nanowire mesh. So it looks like this. We just make it by drop casting on the surface, and we control the density by the quantity of the nanowires in the drop. Then we do an annealing to improve the in-plane conductivity, and we end up with a transparent contact which has a transmittance above 80%. So with this approach, we have done first the blue LED. So you see here an image of the top surface. You have the protruding active nanowires covered by the silver nanowire mesh. And the device indeed can stand the deformations. So here it is bent to a curvature radius of like a little bit stronger than 1 centimeter, but we also bent it to smaller curvature radius, and it can indeed stand these deformations without degradation of electrical or optical properties. We also tried this for a fully transparent blue LED, and indeed it works. If we use the two transparent contacts, we have a little bit less current because probably we miss some nanowires in the membrane with our silver nanowire mesh. However, it works. We produce blue light, and the transparency of this LED is about 60% for wavelengths above 500. So now we want to do other colors. First, we want to do green. So green, if we are dealing with MOVP growth, is a big challenge because it's difficult for this growth technique, which operates at high temperature, to incorporate sufficient amount of indium in the quantum wells to produce green. So in this analysis, we have tuned the temperature of the deposition of the quantum wells to progressively push the wavelength towards green region. And indeed, for the quantum wells grown at 650 degrees C, we achieved 23% of indium in the quantum wells, resulting in the green emission. And here you see the fully green flexible LED produced with these nanowires, with the emission around 550 nanometers. So now we can combine blue and green layers together. We put the transparent blue on top and the semi-transparent green on the bottom. So they are just sealed with a PDMS layer between them, and we can bias them separately, or we can bias both layers together. And depending on where we apply the bias, we can obtain either blue emission or green emission or two colors together. So in this logic, we want to add a third layer on the bottom, the red layer. And by mixing three colors, we can either produce white, or we can think about defining pixels on each membrane and produce some kind of a display. However, we can also think about doing white by monolithical integration of different colors. So on this example, we grew nanowires containing two quantum well systems. First, we grow three quantum wells, which are indium poor and are targeted to emit in the blue. And then we grow 7 quantum wells with a higher percentage of indium to emit green. So on the structural images, it looks like this. So here we have the core on the top. Then you see 3 quantum wells with low indium content and 5 quantum wells with high indium content. You can also see on these images dislocations that start in the indium-rich quantum wells because the lattice mismatch is very strong. So with these structures, we have fabricated flexible LEDs, and you see here the emission spectra. So as you can see, they are peaked in the green, but they are also very large. So we cover blue color and green color. However, the excitation of the green quantum wells in this case is more efficient because they are located closer to the p gallium shell, and since the hole mobility is quite poor, holes are trapped in these quantum wells with high indium content, and it's more difficult to reach quantum wells with low indium content. However, if we push the voltage, as you see on the right, so here for very high voltage, we excite everything and we can start to populate these blue quantum wells and produce two-color emission in this monolithically grown core shell structure. So now, as I said at the beginning, we can, of course, think of white emitters by using these nanowires as a pump. So the nanowires will produce blue light. And as in commercial LED, we will add yellow phosphorus and we will analyze the color quality of the resulting electroluminescence. So for rigid devices, it has been demonstrated by Osram team in 2016. So they used nanophosphorus between the nanowires, and indeed they managed to achieve nice white emission with good color quality. So in our case, we decided to apply the same approach for flexible devices. So we doped nanophosphorus, cerium doped yttrium aluminum garnet in the spaces between the nanowires inside the PDMS membrane. And then we followed the conventional procedure for the fabrication. And we also added a cap of PDMS highly doped with this phosphorus to increase the conversion efficiency. So with this, we obtained devices which are flexible and produce wide spectrum in the electroluminescence. So you see on the top, on the right, the photos of these white LEDs for different bending conditions. And as you can see, the color is white but bluish. So it's called cool white and it's not optimal for lighting applications. So we decided to work on the conversion and on the phosphorus composition. So for that, we try to optimize these two parameters, which are very important for LEDs in lighting: correlated color temperature and the color rendering index. So the first value should be not very high. For the natural light, it's around 5,000. And the color rendering index should be as high as possible, up to 100. So to optimize these parameters, we tried to change the mass ratio of the phosphorus in the PDMS. We also applied different thicknesses of this PDMS capping, and we changed the phosphor inside. So for different samples that are present here, we obtained the best result with the correlated color temperature. So it was, I think, 4,500, and the best color rendering index was 84. Now, indeed, with these flexible white LEDs, by adjusting the phosphorus, we can adjust the color quality. And this is something which can even be modulated on the same device if we apply different membranes doped with phosphorus on top. So to summarize, we were talking essentially about this application for lighting, but the same building block containing these nanowires in the membrane can be used also for other applications. So we can think of defining pixels on these membranes to use them as a display, but we can also do the inverse process. Instead of producing light, we can absorb light and produce electricity for solar cells or photodetectors. And we can also use the internal piezoelectric properties of the nanowires to use these membranes as piezo generators or as pressure sensors. So we indeed tried to produce these kind of devices. So here you see an example of the ultraviolet photodetector. So in this case, we have the nanowires with the absorption starting from 420 nanometers PN junction, and they are again embedded in this PDMS membrane. And with this flexible photodetector, we can have a responsivity of 0.1 amp per watt in the near ultraviolet at 375 nanometers. So this is something which is interesting and important for detection of the UVA, for example, for people and other kind of damage that this ultraviolet can create. We also tried to apply these nanowires to piezoelectric pressure sensors. And here you see an example where we defined by crossed contacts pixels. So on this matrix, we have a 5 by 5 matrix for detection of the pressure. And when we tap on different positions of this membrane, we have a current generation for very small tapping force. So this shows that these nanowires embedded in membranes can be used as flexible and highly sensitive force sensors. Okay, so I think I have maybe 5-10 minutes left, and I would like to present you an alternative approach to these nitride LEDs. So until now, I was talking about producing bottom-up nanowires, which are defect-free. However, we can also think about the opposite thing. We start with a defective conventional layer of nitrides, and we will create holes, very small, tiny pores, at the position where we have dislocations. And like this, we will have this nanoporous layer, which is also some kind of defect-free and which can be used for LEDs. So I will try to illustrate this idea that we have started recently to analyze in the following few slides. So what I propose here is that we start with a standard epi layer of gallium nitride, indium gallium nitride, for example, an LED grown by MOVP. And then we deposit on top self-assembled nanomask with silicon nitride. So this nanomask will partly cover the surface, and the coverage can be controlled by the deposition time. And then the sample is heated up at very high temperature, and then the material, which is not protected, will be sublimated. So with this, we can obtain very different morphologies. You see on these SEM images, porous layers where deposited a very small silicon nitride mask, just 5 minutes of deposition. We increase the masking, so we have more material left. Then we can also have at high masking level just few pores. And finally, if we deposit a fully protecting layer, we do not create any pores. So you can also see how it looks like on the cross section. So here is an example of a gallium nitride layer, and you see these vertical pores which go to different depths. So what is interesting about these layers is that if you take a gallium nitride very thin layer of silicon, which is highly defective and has a very bad luminescence, after porosification, so here we removed 35% of material, we increase considerably the photoluminescence efficiency of this layer. So here the enhancement was more than 3 orders of magnitude. So in fact, this enhancement comes from 2 origins. First, we improve the light extraction. However, the calculations show that this is just ×3, ×5 improvement. But then we also remove defects from the material. And here, the hypothesis that we make is that when we form this silicon nitride mask by just depositing silicon under nitride flux, this mask is preferentially deposited in the regions which are not associated with defects, while the openings are close to the dislocations. So when we sublimate material, we preferentially eliminate these dislocations, which can also start sublimation at slightly lower thermal budget than the normal defect-free material. So we decided to apply this to the full LED structure. So you see on the left the stack. So this is LED grown on silicon with a thin buffer and then a quantum region here. And we also deposited dislocation filtering superlattice before the quantum wells. So this is something quite standard for thin films. And now we have applied the selective area sublimation at 900 degrees C for 25 minutes. With this procedure, we have created 20% of the pores in the material. So you see the SEM top view image here. And also on the bottom, you see the cross-sectional images. By comparing with the reference, we can confirm that indeed these pores are following the dislocation pattern. So dislocations are evaporated first before the other material. And we also observed that we develop a double porosity, so big pores in the buffer layer. And after the dislocation filtering superlattice, we have just small pores, which have a different morphology. So this is something that we started to analyze electrically. So first, we have analyzed the passive structures, so cathode luminescence of the cross-section, where we nicely see the quantum well. We checked the enhancement of the emission, and indeed we observed the improvement of the luminescence efficiency. However, it was not as big as just for gallium nitride film. So for these quantum wells, we have about a factor of 5 to 10 improvement of the efficiency. And we analyzed the electrical properties by using electron beam induced current on the cross section. And by comparing profiles with the reference, we see that minority carrier diffusion lengths and also the depleted region have not changed, which means that this high temperature annealing does not degrade the profile of the doping in the LED. So the p-n junction is there. There is no diffusion, no degradation. And finally, we produced the device. So we need to fill the pores with some insulator to avoid shortcuts. So we deposited Parilene by ALD. Then we deposited a standard top contact with the ITO. And we indeed produced electroluminescent device. So an LED which works. We analyzed the electron beam induced current maps, which are quite homogeneous with some bias due to current collection. And we also have nice spectra peaked in the blue without any shift. However, as you can see on the image of the electroluminescence, we have a spotty signal, which means that our top contact deposited on this parallel passivation is not very homogeneous. So what we're doing now, we are working on the optimization of the current injection in these porous structures, and we hope that indeed we can produce higher and better homogeneity for these porous LEDs. And with this, I would like to summarize my presentation. So I discussed different types of nanomaterials and how they can potentially solve issues in thin film LEDs. So nanowire LEDs are interesting, however, they probably will not challenge the main application of thin films, but they will go in some niche applications such as micro displays or flexible devices. We can use these nanowires in organic films to produce this new functionality of flexible devices at different colors, blue, green, white. We also can apply this flexible technology to other applications. And we can think about alternative way to remove dislocations by doing self-assembled nanomasking and selective area sublimation, in which case we can remove dislocations and create pores and produce electroluminescent devices based on these porous films. I would like to thank the funding sources and thank you very much for your attention.
Thank you very much, Maria. So for this inspiring talk, may I start with my own question? So you mentioned in your talk a possibility to make a 3-cover mixing based on nanowires, but you didn't have red.
Yeah.
Yeah. So red layer was still based on phosphide. Yeah. So now, of course, the question is, can you make indium gallium nitride nanowires with even higher indium content to obtain red emission in order to make 3-cover mixing based entirely on nitrides? Is it possible?
Yes, it's potentially possible. We are working in C2N on MBE growth of these very indium-rich structures. However, by MOCVD, it's very challenging. So we need to change the technique. So we will go for MBE. In this case, it was reported in the literature that the efficiency can be not very bad. So the main issue for high indium content InGaN is the efficiency, because you start to have demixing, and this is difficult to avoid even in the nanowires. So we try to do this. It's very interesting and it's very inspiring, because in this case you have all 3 colors in the same material system, so same processing, same everything, but it's not very easy to do. So maybe phosphides have their place.
Thank you.
Thank you.
Any other question from the audience, please? Yes, Gustav, hi.
Yes, hi. Hello, everybody. So, yes, I have a question for you, Maria. So you showed the improvement. It's about the porous structure. So you showed the improvement of the, I don't remember, was it photoluminescence or cathodoluminescence as compared to the structure without pores? Yes, it's PL. So more than 3 orders of magnitude, as you said. What about the device?
Okay.
If you compare the device after creating the pores and before.
You are absolutely right. So here, this is a kind of extreme case. So you see the structure on the top. You have just 250 nanometers of GaN grown on a very thin island. So it's a highly defective film. So in this case, it's quite easy to improve it by doing whatever. So in this case, you can indeed evacuate these locations and create this huge improvement. If you apply the same procedure to a thicker structure of, for example, 2 microns, where the dislocations are more or less filtered away with a dedicated buffer layer, the improvement is less important. Now, in the device, the issue is, well, first, when we just do the photoluminescence, we have a smaller improvement because already we are looking on the quantum well, and quantum well has a tendency to localize carriers outside of this location. Because in the InGaN layer, you have some fluctuations, and this is well known that even highly dislocated layer can produce reasonable luminescence. So that's why by removing dislocations, you don't get such a spectacular improvement. And then next difficulty comes when we want to inject in this, because now we have something which is highly structured and we need to inject homogeneously. And until now, we have not found the right solution for this, because this stop contacting with the passivation is definitely not the way to go, because we cannot like manage these inhomogeneities. So we are now working on the flip chip where we can metallize continuously this layer with a tilt. And in this case, we hope to improve this electrical part. And we will also try to deposit some passivation on the side walls.
Thank you. Thank you, Maria.
Thank you.
Other questions?
May I ask a question, Maria?
Mm-hmm.
Yes.
This is generally, how deep can the selective evaporation and the tropic evaporation work? You mentioned 2 microns, and when we have an ideal case, say 1 centimeter, but maybe 10 microns, but single dislocation grows from the bottom to the top. Do you expect that we can get some kind of cylinder-like pore?
Well, honestly, we have not tried very deep pores. And the reason is that we are trying to optimize good quality thin films because we want to save material. So our initial purpose is that we will glue just below 1 micron thickness on silicon and we make it defect-free by this evaporation. So now by thinking on this question, I think for 10 microns of GaN, it should work because basically you remove this material vertically, the side walls are stable and the C-plane is not stable. So there is no blocking mechanism. I think you can go quite deep. However, I don't know where the limitation will come from. If you really want to look for 1 centimeter porosification, maybe it will not work. But 10 microns, I'm confident it should work.
This my question is that was motivated after the report of Vladimir Dubrovsky, who explained us this reflection process from the substrate. And when we look on your story, what I would expect that the evaporated atmosphere will stick to the wall of this cylinder, and it's
yeah, I see your point. Yes,
possible
well,
to take cylinder. It must be some very complicated profile.
I see. Yeah, but then in fact we have the opposite thing. We have these M planes, vertical planes, which also can lose atoms. They are more stable than C plane, but we have some residual evaporation. So at the same time, they get slightly broader. So I don't know how this compensation between redeposition and evaporation on the side walls will work. Yeah.
Okay, thank you.
Vladimir should model.
Well, yeah. It's an interesting thing to think of. Yes, but of course, gallium nitride is slightly different from what I presented. Anyway, so any further questions?
Yeah, I have a question, if possible. Yes. Thank you, Maria, for a nice talk. I agree that crucial point for this this last part you mentioned is passivation of the surface, because what you are doing actually, you replace this location by free surfaces. So how are you going to proceed with that?
So indeed, you're right. So we create a lot of free surface, almost same as nanowires. For me, the analogy is quite straightforward. So we were thinking on applying different treatments like ALD deposition of aluminum nitride, very thin layer. Well, basically we did the bibliography on micro LEDs and all the strategies that people apply to micro LEDs. So there are some ways of how they passivate. So I think ALN deposition by ALD was one of the best. And in our case, we have the advantage that these surfaces are self-made. They are not created by ICP, so there is no damage. So these are just dangling bonds, so standard surface, which is a defect, of course. So we were thinking about ALD deposition of different dielectrics to passivate it by surface charge or some reconstitution.
Okay, thank you.
No.
So I don't see any other questions. So let's thank Maria again.
Thank you.
Thank you, Maria. So yeah, the next speaker is Emmanuel Demarquis with a talk entitled Heterostructures and Self-Catalyzed 3 arsenide nanowires, Benefits and Challenges. Please.
Thank you, Vladimir, for the introduction. I hope you can see my slides now. Okay.
Yes, perfect.
So yeah, I mean, after Maria's wonderful talk with a lot of applications in there, I'll take a step back to more basic research, but hopefully this will lead eventually in the future to applications. So I will be talking about heterostructures, both either radial or axial, or both, as you will see, in self-catalyzed 3 arsenide nanowires. Okay. So this will be the structure of my talk. So first I will talk about the core shell nanowires, highly mismatched core shell nanowires actually, how we grow them, the structure, the mismatch in there, and the strain, and how the strain affects the electronic properties like the band gap. This we have already presented a few times, so you may be familiar with this, but I will focus more on our recent findings on the electromobility, how higher it is in the strain core. And then I will move on with gas-all-gas axial heterostructure. We grow them in a pulsed mode. I will talk about the interface sharpness and what's the role of the growth temperature. And the last part of my talk will be what we call complex gallium arsenide quantum dots, which basically we combine the two previous topics, so the core shell and the axial heterostructures, in order to make quantum dots. And hopefully we can, in the end, shift the emission with strain to longer wavelengths close to the telecom bands, as I will talk about later. So the first thing, I will start with the core shell nanowires here. So the first most important basically step is the growth of the gallium arsenide core, which needs to be thin enough in order to have a better chance for strain engineering, and with a low number density to avoid beam shadowing during the following shell growth. So to achieve this, we start with the deposition of gallium droplets on natively oxidized silicon substrates. The number of the droplets is controlled via the substrate temperature. Then we anneal the substrate to a high enough temperature to evaporate these droplets, leaving behind small holes in the oxide. And actually, the size of these holes depends on the temperature and the duration of the annealing step. In the end, we perform the growth, the self-catalyzed growth of gallium arsenide nanowires at a fixed temperature, where the diameter can be controlled in this case via the 5:3 flux ratio. Then on the right side, you see that homogeneous shells can be grown at low enough growth temperatures and high growth rates in order to limit the diffusivity of indium on the sidewalls of the nanowires. If we don't do that and we let indium to diffuse along the nanowires, what we get is these bent nanowires, because indium has a tendency, due to the lattice mismatch, to incorporate mostly on the one side of the nanowire. And this we were able to see in this TM and EDX analysis here. So here you see the compositional analysis of our nanowires using EDX. So you see the blue line is the core, and in this case we have an innerless shell around it. The composition is quite homogeneous. The structure is simplet, as we typically have for self-catalyzed gallium arsenide growth, and the interface shows no misfit dislocations. So here you see a cross-sectional view of the interface, and here you see the interface along the nanowire. So we have no dislocations, and this we could achieve for shell thicknesses up to 80 nanometers, and with indium content in the shell up to 60%. So the misfit is really big. On the right-hand side here, you see a plot from the literature where we have the critical thickness of INGAS on gallium arsenide, on gallium arsenide 111 and 001 here. And here you can compare our data points for our nanowires, and we see that we have exceeded by far the critical thickness of these mismatched layers. I don't know if you see this. So the strain in our nanowires we were able to measure with Raman scattering spectroscopy, and the results you see here. So concerning the shell, the red data points, we have a compressive strain while the shell is still thin, and progressively it relaxes, and basically it reaches to strain-free values after 40 nanometer thickness. On the other hand, the core is tensile strained. The strain increases during the first 40 nanometers of the shell, and then it saturates. So this value up here, we can change further by increasing the indium in the shell. This is what you can see on the right side. So you see the tensile strain in the core increases more and more with increasing the indium in the shell. Okay. So the continuum elasticity theory shows that all individual strain components are spatially homogeneous inside the core, the center, and they're all positive, which means that the lattice expands in all directions, but mostly along the z-axis, the nanowire axis. So this strain asymmetry we were able to find also in our Raman measurements. In the backscattering geometry that we use here, you can see how the nanowires are transferred on another substrate. The TO phonon line from gallium arsenide shifts to the left with respect to the unstrained gallium arsenide because of the hydrostatic strain. From this shift, we can extract the hydrostatic strain as shown in these equations, but also from the splitting between the TO phonons with atomic displacement along the nanowire axis, this TOS, and perpendicular to that, TOD, we can determine the shear strain in our nanowires. And in the end, the values we get out of the Raman measurements are very close to the theoretical ones. From theory, we expect that the increase of strain, of tensile strain in the gallium arsenide core will reduce the band gap. And that's what we see also in PL in the middle here. In fact, the effect is so strong that we reach the 1.3 and the 1.55 micron telecom bands, as you see on the rightmost plot. So besides the decrease of the band gap, the heavy hole, light hole degeneracy is lifted with strain, and electrons recombine basically with heavy holes, which accounts for having polarized PL emission perpendicular to the nanowire axis. So theory also predicts a decrease of the effective mass in the strained gallium arsenide core, the effective mass of electrons, I mean, which could potentially lead to a higher mobility. And on the rightmost plot here, you see our calculations of the effective mass as a function of the indium shell in the indium content in the shell and the corresponding lattice misfit with the core. So to measure the mobility, we used optical pump terahertz probe spectroscopy. So we transfer the nanowires on a transparent substrate for the terahertz. The optical pump of 800 nanometers here generate electrons and holes only inside the core. You can see the band diagram here. So we have the low band gap of the core, which is only excited here. And then a terahertz probe is used with a delay of tau defined here, to drive longitudinal plasmon oscillations along the nanowire axis, which produces this characteristic resonance in the real part of the relative photoconductivity. So the peak frequency here is related with the electron concentration inside the nanowires, and the peak width with the momentum scattering rate of electrons or the corresponding mobility. So down here, you see these relations, the plasmon frequency related to the concentration of electrons, and the scattering rate, gamma, related to the mobility. So in that way, we can analyze our nanowires. Before I move on, though, to the results, we found that this resonance, the resonance width, which is basically the mobility, depends on the number density of the nanowires on the probe sample. So you see this example here with measurements on the same sample, but on different positions where we have a different number density of nanowires. So the filling factor is higher for the red than for the blue. And you see that we have a larger width, which will lead to an overestimation of the scattering rate, so an underestimation of the mobility. And this is explained, basically this effect is explained with these COMSOL simulations that we did. So we found that if the nanowires in a dense sample, they touch each other, and this we see in this SEM image. Here, for example, we have two nanowires side by side. In the other case, they are in a row. So for these two particular geometries, we have calculated the photoconductivity resonance, and we see that it shifts either to the right or to the left. And of course, if we measure a sample with many nanowires there, then we have, as a result, an asymmetric spectral broadening. So to alleviate, to avoid this problem, we have to measure very sparse nanowires, so samples with very few nanowires, although this goes to the signal to noise ratio, of course. So here we see the results. This is the plasma frequency as a function of time and the corresponding electron density. We could fit the time dependence of the concentration with a mono-exponential decay function, and we extracted a characteristic lifetime of 190 picoseconds. Now, using this characteristic lifetime in this formula here, and plugging in the lifetime of bulk gallium arsenide from the literature, we were able to extract the recombination velocity S of electrons at the core share interface for the given radius of the nanowire, which is in this range, 4,000 centimeters per second, which is comparable to really high quality lattice strain-free interfaces. So this is a good sign about the quality of our interface. And then on the right side, you see the scattering rate of electrons as a function of time, and then the corresponding mobility values. You see that these values, they don't change much with time. So we have a mobility around 5,000 centimeters square per volt second. So let's see now the big picture here. Here I plot the scattering rate and mobility again versus the concentration of electrons. And I will start with the bulk gallium arsenide measurements, again with optical pump terahertz probe spectroscopy. And these data are from the literature. And the measurements are done at room temperature. So typically, the dominant electron scattering mechanism is the scattering by LO phonons, this gamma P here. In OPTPS, though, we photogenerate equal concentrations of electrons and holes, which makes the electron scattering by holes equally important. This is defined by gamma H here. So checking now the data for bulk gallium arsenide, we measure the total gamma, the total scattering rate, and taking the scattering rate by phonons from the literature, and using this equation here, we can extract basically the scattering rate from holes, which is again an inherent issue that we have in OPTPS, optical pump terahertz probe spectroscopy. And we see that it's quite comparable with the scattering by phonons. So very important for us. Now, I move on and I will add data points from all-gas nanowires that we measure, where of course the lattice mismatch is negligible, so the gallium arsenide core is unstrained in this case. So we see that we measure scattering rates very similar to those of the bulk, despite of the scattering, of course. And if we assume that gamma P and gamma H are similar to those in bulk gallium arsenide, then we can conclude that the scattering of electrons from the interface, this gamma I factor, which also goes in the equation, must be negligible compared to the others. So this is again a good sign that the transport properties of electrons not affected by the core shell interface, which is of course very reasonable because we excite longitudinal plasmon oscillations, which means that electrons move along the nanowire axis, so parallel to the core shell interface. Finally, also the strain nanowires show similar scattering rates. The decreased effective mass in the strain gallium arsenide is expected to reduce the scattering rate from phonons, but also increase, on the other side, increase the scattering rate by holes. And actually, these are very comparable. So in the end, they cancel each other. That's why we get similar scattering rate with the bulk gallium arsenide or the unstrained nanowires. However, even if we have the same scattering rate, now we have lower effective mass for electrons, so the mobility values are higher. We see an increase of the order of 30%. I said before that this scattering by holes, the gamma H factor, is inherent of the optical pump terahertz probe spectroscopy. So if we set it to 0, as it would be in the case, for example, for a transistor, then we can translate these values to something more realistic. So we see the typical values for bulk gallium arsenide, close to 9,000 at room temperature, the same for the unstraight nanowires. But then for the strained, we get an even higher enhancement of the order of 50%. So after all, we believe that the strained nanowires are promising for high-speed, low-power transistors on silicon, as you can see here, for example, in this plot of different materials with different effective mass and mobilities, of course. So you see that we can combine our nanowires with the lattice mismatched silicon here without any issues. But of course, one could say that a more natural choice would be to grow InGaAs nanowires directly on silicon. But this is difficult if we don't use gold catalyzed VLS, because we know, for example, that the selective area growth of InGaAs nanowires on silicon comes with many stacking faults there. Or another approach would be gallium catalyzed gallium arsenide nanowires, trying to incorporate indium in there, which is also difficult. The most promising could be the growth of indium catalyzed InGaAs nanowires, but this is not very mature for the time being, at least. So I will move on now with the axial heterostructures. So I will refer now to work from the group in France, Harman, Priante, Glass, and the others. They were the first to publish results on gas axial heterostructures in self-catalyzed VLS-grown nanowires. So they showed that it takes several monolayers. Let me describe first the first image, where you see a nanowire with AlGaAs insertions inside the gallium arsenide nanowire. They did HADF analysis, and from the contrast, they could extract the aluminum arsenide fraction inside these insertions. So they showed that it takes several monolayers, as you can see in these profiles, to change the aluminum from the minimum to the maximum value. So the sharpness of the first interface was improved after interrupting the growth and pre-filling the gallium droplet with aluminum. And you see this improvement down here, which was quite significant, and they achieved very sharp interfaces. But the second one remained much thicker. So Glass and Dubrovsky explained the specific composition profiles as a result of the thermodynamic equilibrium between the liquid and the solid phases, the so-called reservoir effect, where the aluminum arsenide fraction in the nanowire crystal has a specific relation with the concentration of aluminum inside the droplet. So they predicted that this second interfaces, there is a chance to make it sharper if we decrease the radius of the nanowire or decrease the temperature of the growth. So influenced, basically inspired from these results, where it's clear that it's necessary to have growth interruptions and low temperature growth. This actually fits very well with the pulse growth mode that we developed back in 2016. We call it actually droplet confined alternate pulse epitaxy. Of course, it's MBE, but we use alternate pulses of gallium and arsenic. So they're never supplied together. So the diffusivity of gallium is much better in this case. So we have a good chance to grow at much lower temperatures, even in the range of from 350 to 550 degrees, which is much lower than the typical higher than 600 degrees Celsius. With the pulse growth, of course, we can interrupt without any stacking faults, and we can lower the growth rate down to the monolayer scale. So we have very good control. Here you see a scheme of the growth pulses where we have the alternate supply of gallium and arsenic. And on the right-hand side, you see the growth of gallium arsenide nanowires in the pulse mode directly on silicon substrates. Here is the the TEM of a representative nanowire, where you see that we can barely find any stacking faults, maybe at the very bottom or the very top. So the idea now with the ALGAS insertions is to supply also some aluminum pulses in between the others. And in fact, we can control the amount of aluminum in the insertions by controlling either the duration of the pulse or the aluminum flux. We do the analysis as Priant et al. Did in the past. So we get HADF images. We analyze the contrast. You see these oscillations. Each period corresponds to one monolayer thickness. And from the intensity ratio, and using this equation here, we can extract the aluminum arsenide fraction in the crystal. And the only thing that is missing here is this gamma parameter, which comes from calibration measurements based on EDXS. On the right-hand side, you see an example from this, the analysis, the results from this insertion here, where you see the aluminum fraction in a monolayer by monolayer analysis here. And of course, by integrating this curve, we can deduce the total amount of aluminum incorporated in the insertion. Now, this total amount of aluminum in the insertion we can compare with the amount of aluminum that we offer during every pulse. So this we can do by using this equation here. It's pretty straightforward. The number of aluminum atoms is equal to the surface area of the droplet, which is interceptable by the beam of aluminum, times the flux, the effective flux of aluminum, times the duration of the aluminum pulse. And here you see this surface area of the droplet given as a function of the radius and the contact angle beta. Basically, we know all these parameters except the radius of the nanowire and the contact angle that we can basically measure. The radius we can measure directly from TEM. Beta we can extract, calculate indirectly from the growth rate of the different segments inside the nanowire. So if we compare this value of aluminum with the theoretical one, we find a very good agreement. So we have done that for many different insertions, 30 different insertions, either in the same nanowires or different nanowires with different supplied aluminum. And you see that the incorporated aluminum in the crystal is equal to that. So the slope of these curves is 1, which means that negligible aluminum diffusion, we have negligible aluminum diffusion from the sidewalls to the droplets. So here you see that if we vary the flux of the aluminum, as I said before, or the pulse duration, we can change the amount of aluminum inside the insertion. What is very interesting here is this superlinear increase of aluminum at the first interface that reaches a maximum rate here of 0.20 monolayers. This means 20% of aluminum per monolayer, which is quite sharp. We try to understand why is that, and basically this behavior resembles the lower part of the sigmoidal profiles described by Luna et al. In this publication here. Basically, such profiles, such sigmoidal profiles, have been correlated with the two-dimensional island growth, like we have in nanowires, with a composition-dependent coefficient. And this is the key point here. So what we believe is that also in our case, the incorporation of aluminum in a growing monolayer depends on the aluminum content of the monolayer below. That's why we have this superlinear increase. Then the second interface is also quite sharp, as expected for this relatively low growth temperature of 550. However, if we compare it with theory, and here I have used Vladimir's model for this liquid-solid equilibrium, we see that in this case, a much sharper interface is predicted. So most likely, this deviation here means that we have additional mechanisms that limit the sharpness of the interface, of the second interface. So I told you that with a pulse growth mode, we can go to really low temperatures, and that's what we show here. We reached down to 350 degrees with the blue data points here compared to the 550, and you see that we have a further improvement of the interfaces, so they become sharper and of course also more symmetric. So also the second interface becomes very sharp, but still there is not good agreement with theory, with a liquid-solid equilibrium theory. So this brings me to the last part of my talk, where we want to grow quantum dots using the core shell and the axial heterostructure that I described before. So as a general slide here, I compare the traditional, let's say, quantum dots that people have been growing on thin films for many decades now. So they use typically the most popular ways to grow such the quantum dots is the Stranskika-Stanov growth mode, where we have the strained material growing on the substrate, and then we have this relaxation mechanism. So we have in the end the wetting layer and the relaxed quantum dot on top. Droplet epitaxy has also produced very nice results. And I think most recently, very impressive results concerning quantum dots have been produced with droplet etching and filling. But still, nanowires, in principle, they offer some advantages that you cannot find in the other methods. So we can independently control the width and the height of the quantum dots. We can have different quantum dot barriers in the axial and in the radial directions with loose lattice mismatch restrictions. We can control the number of quantum dots deliberately and the spacing between them. So for single nanowires, of course, we can have single photon sources operating on demand. The shape of the quantum dot can be very symmetric, which will, in principle, can help with the emission of entangled photon pairs. And of course, we can grow them epitaxially on silicon. So here you see a plot which summarizes the state of the art of quantum dots in nanowires. Here we use the second order correlation function as a measure of the quality of the nanowires, of the quantum dots, I'm sorry, versus the wavelength. So here we use different colors for different growth modes and different symbols, shapes for different substrates. But it's easy to see that the telecom band, the space there is quite empty. So there is a lot of room to try with our nanowires. So that's the motivation of our work. So as I told you before, we use gas-algas nanowires grown in the pulsed mode. Since pulsed mode means that we cannot keep the aluminum content in the algas barrier constant, what we do here is we use superlattices. So a series of closely spaced algas insertions. Then we have the gallium arsenide quantum dot, and then the second superlattice. Here is the corresponding EDXS analysis, where you see the average aluminum content of each superlattice. And then we cover with a shell, this quantum dot with a shell. This can be either algas for unstrained nanowires or inalas, as I showed before, for tensile strained quantum dots. Here are some photoluminescence results. You see the black curve is with the algas, quantum dot with the algas shell, so unstrained dot, and the red one is the one with inner shell, so it's the strained one. The dimensions here are different, so they cannot be directly compared. But what I want to show here, and this is clear, is the effect of strain. So it shifts the emission peaks. So the thick one comes from the gallium arsenide stem below the quantum dot, and this is the quantum dot. So they both shift to lower energies due to the tensile strain. And actually, these numbers, the emission energies, fit very well with what theory predicts. And now I will add a very preliminary result. So if you see here, the temperature is relatively high still. So now, very recently, okay, I will stay a bit just to describe this plot. So you see for the red one, the quantum dot emission blowed up here. You see that the full width at half maximum is not that small, which is desirable, of course, for a quantum dot. So this is a very preliminary result from basically a few weeks ago, where you see a quantum dot where the superlattice was grown at 350 degrees, where we have much sharper interfaces. And you see already here that the peak is much thinner compared to the others. And here in this blow up, you see basically that although we have two peaks, they are very thin in the micro EV scale, a few hundreds of micro EV. And but of course, before you start complaining, we may call them quantum dots, but for now it's more like quantum disks, because if you see the diameter is quite large, so there are more quantum disks. And basically, in order to understand where all these peaks come from, we are planning to use much thinner nanowires now, in order hopefully to get rid most of them and remain with a single peak, narrow peak. Here is polarization-dependent photoluminescence, where you see that for the strained nanowires, because electrons recombine with heavy holes, the emission is polarized perpendicular to the nanowire axis, while the emission from unstrained gas quantum dots with algas shell, the emission is polarized along the nanowire axis. So this is all I want to talk about. So I hope I convinced you that it's very important to grow thin gallium arsenide on silicon substrates, and this we managed to do with treatment of the substrate prior to the growth with gallium, which maybe I forgot to mention. This is a very reproducible method, which is very important for detailed studies of big series of samples. Then we grow the mismatched in-gas or in-alas shell without any defects around the nanowires, and we suppress the bending of the nanowires by using kinetically limited growth conditions. The gallium arsenide core is heavily strained, can be heavily strained, with a great effect on the band gap, which we can narrow down to the telecom bands, and the enhancement of the electromobility, which is 30 to 50% higher than the bulk gallium arsenide. Concerning the axial heterostructures, we used pulsed growth for that, and we were able to grow quite sharp interfaces and nice superlattices that we later used for the quantum dots. The quantum dots that basically we call them complex because you will use different materials for the axial and the radial barriers. And the nice thing is that we have a lot of freedom to design the electronic properties of these quantum dots, and also use strain engineering to shift the emission, hopefully down to the telecom bands. So what comes next is to use thinner nanowires and more strained, of course. So before I finish, I would like to acknowledge all my collaborators, and of course, thank you for your attention.
Thank you very much, Emmanuel, for this nice talk. So can I start with my own question? So you mentioned this aluminum pulses to grow gas or gas axial heterostructures in many ways. And then one of the conclusions was that the all-gas-gas interface wasn't as sharp as predicted by the model, and also even if we compare with Jean-Christophe's and Frank paper, it wasn't as sharp as in their case, because I think the modeling and the experimental results in that paper correlated with each other. And you mentioned some additional mechanism for broadening the interface. So what is the mechanism? What do you think? Low temperature, or I don't know.
If I knew, I would have written it. We don't know. For now, we don't know what's the,
you don't know.
the reason.
But there is a big difference. So yeah.
Yeah. There is a significant difference. Of course, the prediction of theory is very, very impressive. So here it predicts that we can go from 60% of aluminum down to 0 in 2 monolayers.
Yeah.
Which, yeah, I don't know in reality if this is ever possible.
I see. Thanks.
And I always had in mind, because in the past growth, we use continuously growth interruptions. So I don't know if during these interruptions we have some back diffusion of aluminum from the crystal to the droplet. So what we were planning to do soon would be to test the effect of the growth rate, so the arsenic flux. If we grow faster, if we are able to freeze the aluminum inside the crystal,
yeah, you may suppress the diffusion by increasing the arsenic. Yeah, I see. Thanks. So any other questions from the audience, please? Yes, Frank?
Talking about the other interface, I think you mentioned that there might be an effect of the underlying, talking about the same gas heterostructure, of the underlying nanowire onto the incorporation into the growing monolayer. Can you elaborate a bit on this, please?
Basically, the way we grow them is that we grow gallium arsenide, then we interrupt growth, and we fill the droplet only with aluminum. So at time equal to 0, we have the maximum aluminum concentration in there, right? And then we start supplying only arsenic. And that's when the growth starts. And although we have the maximum concentration at T equal to 0, the maximum concentration of aluminum, we don't have a sharp increase as predicted by your model, for example, or Vladimir's, but we have this superlinear increase. And to my mind, at least, this superlinear increase can only be explained by a sticking coefficient of aluminum, which depends on the pre-existing aluminum in the crystal. Actually, this is what is shown by Luna et al. On the right side. And of course, this was for vapor solid growth. So there was no droplet liquid phase involved. So, but for us, the similarity of the shapes is quite obvious. So we believe that they might, we might have, maybe this is the reason of our interface shape.
So you're thinking about aluminum sticking to the top facet and diffusing along the interface to the growing monolayer, is it, or am I going too far?
Yeah, I mean that could be only guessing, but of course this model here describes sticking of aluminum on top of the island, and then diffusion to the edges and incorporation there. I don't know how similar it can be in the nanowires. We've seen publications recently. Basically, this is an old story coming from a few years ago, but I think von Kuberta showed it nicely recently with this ordering of the liquid close to the interface. This could also affect the incorporation. We don't have we have many ideas, but we don't have a clear understanding of what's going on.
Thank you.
Further questions? Yes, please. I see two more questions, so please go ahead.
Yeah, okay, thank you, Vladimir. So thank you, Emmanuel, for the nice talk. So I was really impressed by the shift that you can obtain for the gallium arsenide emission, just playing with a strain. So do you know what are the limits? So
the limits for now is our setup. So if I go back, the PL setup, I mean. So let me go past here. So here we increase the indium in the shell, the inner last shell, and the core gets more and more strained. So far, we have reached up to 66%, if I'm not wrong. And Raman shows that this linear behavior keeps going. So this suggests that we have no plastic relaxation yet. So the strain is higher, but unfortunately now the band gap must be below our index detector. So at least for single nanowires measurements, we are a bit stuck because our setup doesn't support that. We will try with a macro PL setup, but again, in this case, it becomes a bit tricky to understand what's going on. But I would say that from the strain point of view, from the Raman measurements, it shows that we can keep going to higher strain, but we haven't measured still the actual band gap.
Okay, thank you. But you know what are the limits from the point of view of dislocation generation?
No, we have observed dislocations for a shell with 74%, if I remember right, of indium. Mm-hmm. But there is, a gap between the 65 and the 74 because we didn't do many small steps there. So it must be somewhere there, the limit for the given core radius, of course, which is in the around 20-22 nanometers, the diameter, I'm sorry.
Okay, thank you very much.
Yes, please go ahead. I have seen one or two more participants raising hands. Please go ahead with questions.
Yeah, thank you very much for a nice talk. I guess maybe a couple of short questions. So as I understood, coming back to this aluminum concentration, as I understood, you used the model and you compared the modeling, which does not take into account any strain effect and any elastic energy. Or
you're talking about this model here?
Yes, as I remember. Is that true?
Yeah. I mean, here we consider that the misfit between gas and gas is negligible, right?
It's zero, yeah.
Strain effect is not taken into account.
It's not counted here.
The shell comes later, but this doesn't affect the shape of the interfaces here.
Yeah.
Okay, thanks. And maybe a very short question is about this pulsed mode. Or did you try to grow other free fives? I don't know, indium arsenide, gallium phosphide, or is mainly about gallium arsenide?
Yeah, phosphorus we don't have in our system. So
Okay.
we have tried with indium arsenide. Vladimir knows that.
Okay.
It's possible. It's also nice because you have a good chance to control the contact angle with the pulsed mode. So to control the crystal phase of indium arsenide, but we haven't done much there. Not yet.
Okay. Okay. Thank you. That's interesting.
All right. So I think we should thank Emmanuel again. Thank you very much. So yes, our next speaker is Alexei Zhukov.
Yes, I'm here, Vladimir.
Hello, with a
Nice
talk
to see you.
entitled Quantum Dot Micro Lasers for Integration on Silicon.
Okay, just let me share my screen. Dear colleagues, dear friends, I'm really very happy to see you on the screen of my laptop.
Me too, yeah.
Yeah, so distantly, unfortunately, but nevertheless. My presentation will be about micro disk lasers with quantum dots. So I will talk about some basic ideas why we're interested in micro disks and how it's possible to combine some advantages of micro disk lasers with, for example, non-native substrate like silicon. In different parts, this work was contributed by many organizations, many universities, of which I would mention the first one, of course, academic university, Yoffie Institute, and many different organizations. And let me point out that my affiliation now is not the Yoffie Institute and not the academic university, but High School of Economics in St. Petersburg. It doesn't mean that we are ready to bring all our ideas to the market, though just High School of Economics also interesting in physics, and here we organize a new laboratory devoted to optoelectronics. So the name of the laboratory is Quantum Optoelectronics Laboratory. Mostly focus on small signal modulation analysis, time result spectroscopy, temperature dependent measurements, and so on and so on. So also a laboratory from High School of Economics also involved in this research. So let me try to explain why we're interested in micro lasers, because the conventional semiconductor lasers are quite large. So the typical cavity length of a stripe laser is millimeter or even longer than millimeter. But if we take into consideration that the diode laser requires heat sink, which can be very massive, so the real size of a device could be not millimeters but centimeters. Of course, this large size is not compatible with some important applications, for example, sensors, some short-range optical communication, and some others. So it's the size of electronics and size of optoelectronics are very, very different. So people are thinking about micro lasers, and the first device which is should be mentioned here is VCSEL, vertical cavity surface emitted laser. It's very I would say mature device. It's already demonstrated the possibility of for example, high-speed modulation with the speeds more than 30 gigabits per second, very low power consumption, less than 1 picojoule per bit, and so on and so on. But there are also many disadvantages of VCSELs, which is associated with it's complicated epitaxial structure which required very thick distributed Bragg reflectors and very precise compositional thickness control of Bragg reflectors and the cavity. Also typically oxidation is required, which also needs some precision in fabrication. And what's also important that if we are thinking about integration of a laser with some other photonics or electronics, it is better to have light emitting in the plane, not in the vertical direction. So if we are thinking about integration of VCSEL, one need to also incorporate some additional micro optics like prisms or something like this in order to move back the emission from the VCSEL. And finally, one more disadvantage that typically the wavelengths of emission in the VCSEL are limited. It's typically shorter than 1.1 micrometer. So we are thinking about easier devices, not so complicated, which means that the fabrication is very simple and potentially this corresponds to very cheap fabrication processes. But of course, we should understand that the properties, the behavior, the device characteristic could be a bit worse compared to VCSEL, for example, but the structure itself are very simple. So it was our thought, and we are looking into the microdisc laser geometry. So in this case, the whispering gallery modes, which is propagates like shown here in the periphery of the microdisc resonator, that doesn't require some additional distributed Bragg reflectors or some additional deposition of highly reflective dielectric coatings or something like this, because it's simply associated with internal light reflection in the cavity. As a result, the very high Q factors or low radiation loss can be achieved in microdisc lasers, even if its size is comparable with the cavity, with the length of flight, even if the diameter of, for example, 1 or 2 micrometers, without any additional complicated processing. So why we use quantum dots as a negative region is quite simple answer, because quantum dot laser already demonstrated the applicability for low threshold application. For example, the record low threshold current density for quantum dot lasers is just 10 amps per square centimeter, and high temperature stability can be achieved with a quantum dot, which is important for heat-sink-free operation. Also, quantum dots can shift the emission wavelengths towards 1.2 or 1.3 micrometers at room temperature. So this means that some media, for example, silicon, becomes transparent for this emission and can be integrated with such lasers. Also, it is important that quantum dots are very insensitive to different sorts of defects. For example, defects associated with epitaxial growth. So, for example, if the epitaxial structure is grown on non-native substrate, for example, 3,5 on silicon, lots of epitaxial defects still exist in the active region, and the quantum dots remains unsensitive or less sensitive compared to quantum wells. Herein this demonstration how the threshold current density of quantum dot lasers grown on silicon improves from year to year. It is seen that now the large macro lasers with quantum dots already or nearly reach the level which was already previously achieved for quantum dot lasers grown on a native gallium arsenide substrates. So what is also important for micro laser application is that the quantum dots are also insensitive to surface recombination. So if one need to fabricate micro cavity like micro ring or micro disc, it is necessary to etch deeply the epitaxial structure through the waveguide and through the active region. In the quantum well case, a very serious non-radiative surface combination exists on the side walls and make it difficult or impossible lasing if the size of the device is micrometers. In case of quantum dots, and that was demonstrated maybe more than approximately 20 years ago already, it is possible to etch through the quantum dot plane, and very little effect on the threshold current density can be achieved. So some examples of microdisk lasers fabricated by us with a very small diameter, as small as 1 micrometer or few micrometers, so-called suspended microdisks, and it is possible to achieve lasing in such very small cavities, even if the diameter is as low as 1 micrometer. It's lased at room temperature. The lasing wavelength is roughly 1.3 micrometer because we use indium arsenide, indium gallium arsenide quantum dots. And herein some explanation that in addition to radiation loss associated with a disk shape of the resonator, which is low until 1 micrometer and then rapidly increase, there is some another sort of optical loss associated with light scattering, with roughness of side walls, which is slowly increases with decreasing the diameter, and actually the smallest diameter where lasing is still possible is achieved as a combination of is achieved because of gain saturation. So the quantum dot gain is limited, and in a small devices, optical loss becomes very high to be prevented, to be overcome by quantum dot gain. But optically pumped cavities, like shown here, it's interesting to study some physics, some effects inside the cavities, but for application, it's more convenient to use electrically injected, electrically pumped lasers. So herein some micro photo of arrays of quantum dot lasers, which we study and fabricate using dry etching. The structure is very simple. It's very similar to what is used for fabrication of edge-emitting lasers. No thick break reflectors, just waveguide inserted between claddings and several planes of quantum dots inside the waveguide. So here is some summary of threshold current density as a function of the diameter for different sorts of the active region. Herein I demonstrate in red Stransky crosstown of quantum dots, indium arsenide, indium gallium arsenide, which is capable of emitting around 1.3 micrometer, and this sort of microdisc lasers demonstrate the lowest threshold current density, which is less than 300 cents per square centimeter. So compared to this sort of microdisc lasers, quantum well as an active region demonstrates very high threshold current density, more than 1 order of magnitude higher. So we attributed this to a very fast carrier diffusion along the active region plane. So in the case of quantum well, electrons and holes can recombine non-radiatively at the side walls. So that's the reason why quantum wells are not so suitable for microdisc and microring application. And herein also I demonstrate some other sort of the active region, which we call quantum well dots, and I will explain a bit later what this means. So, and you see that the threshold current density is very comparable to threshold current density in quantum dot based microdisc lasers. Why we introduce some new sort of the active region. So in case of quantum dots, the advantages for micro laser application is a short carrier diffusion lengths, which suppress surface recombination at defects and at site walls. But the disadvantage is broad gain spectrum, which is associated with non-uniformity of quantum dots and typically results in multi-mode lasing. And another disadvantage is low density of states, which results in low maximum gain, optical gain. So in case of quantum wells, there is no such a problem, but as I mentioned before, very fast carrier diffusion leads to impossibility or to very high threshold current densities in case of small devices. So we would like to combine somehow advantages of quantum dots and the advantages of quantum wells in a single active region. And it was found that it is possible when depositing by indium gallium arsenide on a gallium arsenide with some small misorientation. This misorientation is approximately 6 degrees with respect to 001 exact crystalline plane. And this misorientation in combination with some growth regimes of during massivity deposition results in transformation of uniform indium gallium arsenide layer into some non-uniformly distributed islands. So what we call quantum well dots is just some roughness, some fluctuations of thickness of quantum wells, which can be observed in the plane view TM images and also in the cross-section TM images. So compositional non-uniformities and in combination with surface corrugation. So the total surface density of these islands are quite high, 1 order of magnitude higher compared to conventional surface density of quantum dots. So it is expected that the gain will also be high compared to Stransky-Krastanov quantum dots. Also, it is important that this sort of quantum well dots can be stacked many times. It is important maybe not for lasers, but for such devices like photodetectors or solar cells and so on. But in case of quantum well dots lasers, we typically use several planes of quantum well dots between 3 and 6 typically. So there's some comparison of optical gain per layer as a function of current density per layer. One can see that, of course, the transparency current density is higher because the surface density of islands is higher in case of quantum well dots, but also the saturated gains, the maximum gain is also several times larger for this new sort of the active region. So broad area lasers demonstrate very little nonlinear gain saturation with and very high optical power can be achieved, and the broadening of the lasing wavelengths of the laser spectrum is not very high, which demonstrates that high density of states in these quantum well dots. So returning back to my story about microdisc lasers, is it to plots demonstrate why quantum well dots have certain advantage over conventional quantum dots when using as an active region of microdisc layers. You see that in the case of quantum dots, the emission associated with whispering gallium modes are very weak. So in the total emission of quantum dot based microdisc layer, the the lasing emission typically takes only a few percents. Everything else is a spontaneous emission from the ground state and many excited states, which is typical for quantum dots. In case of quantum well dots, the lasing emission are much brighter compared to spontaneous emission, and also much brighter compared to lasing emission from Stransky-Krastanov quantum dots. So in case of quantum well dot, the side mode separation ratio is easily to achieve, for example, 30 or even 35 dB, which is impossible in case, or very difficult. Maybe some additional measures should be undertaken in case of Stransky-Krastanov quantum dots to suppress other optical modes. In case of quantum well dots, it's easy to achieve. So what is also can be achieved using quantum well dots is relatively high output power. So you see that the output power achieved the level of several milliwatts, which is untypical for microdisc lasers, because usually people think that in a disc laser, microdisc laser, all optical power is concentrated inside the microdisc and nothing goes outside. So it is not so, and we think that probably quantum well dots acts as a scatterers for the light and results in a very efficient emission of laser power outside the microdisc. So the total intensity of the lasing dominant modes very close to 100% from the all power emitted by microdisc laser. Not only by compared to spontaneous emission, but compared to all lasing modes. What is also important is that the microdisc laser with quantum well dot active region can operate at very high output temperatures. For example, here it is demonstrated that lasing is still possible even if the temperature is 110 degrees C. And if we summarize the property of microdisc lasers, their maximum operation temperature and diameter, it is seen that the smaller the diameter, the lower the operation temperature. So we attribute this to the fact that in addition to ambient temperature, there is some self-heating of microdisc laser because of Joule heating and heat removal becomes non-efficient with decreasing the diameter of the device. So that's why in small devices the maximum temperature is lower as compared to larger devices. So it is possible to modulate the emission of a microdisc laser with relatively high frequency. Here it is demonstrated that the maximum modulation bitwidth can be approximately 7 gigahertz. It is sufficient in order to use microdisc laser for optical data transmission with bit rate at least 10 gigabit per second, as shown here. So the eye remains open for this bit rate. And what is also important is that this sort of microlasers can operate without any temperature stabilization, without external heat sink, because, for example, modulation response with temperature stabilization and without temperature stabilization are very similar. So there is no need to use large heat sink to stabilize the temperature of the microdisc laser. So what is also important that the power consumed per single bit is quite low. There's about few picojoule per bit, Of course, it is higher compared to the VCSEL, but very good for other sorts of microdisk lasers. To my best knowledge, this is the smallest energy consumption demonstrated for microdisk lasers of any kind. So one of the prospective application of micro lasers is their combination with silicon, for example, for short-range optical communication, for example, as shown here, to provide optical link between, for example, processor and memory and some other related applications. And in case of silicon, all necessary photonics can be made of silicon or silicon compatible materials. So the main problem is the lack of efficient laser. So you know that the main problem of growth of 3.5 materials on silicon is a difference in lattice constant and difference in polarity, and also difference in temperature coefficients, which results in cracking the epitaxial structure grown on the silicon. So this can be a problem, for example, for stripe lasers, because this cracks and the dislocation leads to very poor properties of can lead to poor properties of large area lasers. But in case of microdiscs, it is possible to locate a device in the area where no cracks and no defects. So, and the properties could be similar to properties of a microdisc laser on a native gallium arsenide substrate. So this micro image of arrays of quantum dot based microdisc lasers grown on silicon and fabricated from the epitaxial structure grown on silicon. And here is some summary of the threshold current density as a function of diameter for various groups, including our results. And here we demonstrate the lowest threshold current density among different approaches, different microdisc or microring lasers made of epitaxial structures directly grown on silicon. The threshold current density is smaller than 400 amps per square centimeters, which is, to my opinion, very good. So the reproducibility of parameters for microdisc lasers made of epitaxial structure grown on silicon are very reasonable. For example, the distribution of operation voltage is very small, less than 5%. The distribution of output power, it's not the total power, it's just power measured by photo detector and at some standard location. The deviation is higher, approximately 20%, but it's also quite good. This demonstrates the reproducibility of fabrication process, and the quality of epitaxial structure cells is quite high. We also undertake a preliminary reliability test for quantum dot microdisc laser made of epitaxial structure grown on silicon, and the estimated mean time to failure is estimated 80,000 hours. It's also not very bad, but still definitely some additional work is required to improve the lifetime. So you see that the epitaxial growth of 3.5 materials on silicon remains tricky, and the dislocation density is still quite high. So the alternative approach could be a hybrid integration of 3.5 optoelectronics with silicon substrate. When we grow separately 3-5 epitaxial structure, made array of microdisc lasers or whatever, and then transfer the array or single device onto a silicon chip. So we choose this opportunity as well on a silicon in a silicon wafer, an array of contact pads with some conductive paths are fabricated, and after that, the chip comprising several microdiscs are transferred onto silicon using gold thermocompression. So here in the micrograph, where quantum dot micro laser is transferred onto silicon, and what is also important, then the distance between the silicon wafer and the active region is quite narrow, just 2 or 2.5 micrometers. So it is very convenient for integration with some other devices, because narrow thickness is important for this. So because of very high thermal conductivity of silicon, we observe improvement of heat removal from the active region as compared to the same microdisc laser just fabricated on a gallium arsenide. The decrease of thermal resistance is roughly 2 times. Here in blue is demonstrated the microdisc lasers on a gallium arsenide substrate, and in the red some microdisc lasers here hybridly integrated with silicon wafer. Improvement in thermal resistance results in improvement in output power, which is in the best case reach 25 milliwatt in CW regime without any external cooling, external temperature stabilization. So the rollover test, this means that we apply high DC current, then switch off the current and apply DC current again, and you see there is no difference in the first, second, and third, and some other measurements. This means that no degradation in the device, everything is very reproducible, even if the maximum current density is more than 20 kiloamps per square centimeter. Dynamic characteristics after hybrid integration slightly improves compared to initial microdisc lasers on a gallium arsenide. The highest modulation bandwidth is approximately 8 gigahertz, and we attribute this also to improvement of heat removal from the active region. And finally, it is possible to combine microdisc with a photodetector, for example, and here is some preliminary demonstration that modulating the current applied to the microdisc, it is possible to modulate photocurrent measured by a photodetector. So it's some demonstration that it's possible to use this microdisc and micro photodetector pair, for example, for sensing, something like this, for short-range optical communication, and so on and so on. So it is interesting to estimate the maximum possible modulation bandwidth from the K factor extracted from the damping factor and relaxation acceleration frequency. The K factor was estimated as 0.4 nanosecond for 30 micrometer in diameter lasers. This means that the modulation bandwidth limited by K factor is approximately 20 gigahertz. It's quite high. Interesting that for smaller microdisc lasers shown here, the K factors is even lower, and the modulation bandwidth can be estimated as high as 50 gigahertz. It's very high. So let me conclude. My conclusion are quite simple. So the microdisk lasers, it's a conventional combined conventional laser gate structure and simple post-growth processes, which is important for mass production as when we are thinking for future application. Quantum dots are important because they provide long wavelength emission and reduce sensitivity to epitaxial and non-epitaxial defects. And then overall, quantum dot microdisks looks like competitive solution for short-range optical communication, compatible with silicon-based components for sensing and for some other applications. So that's probably all. Yes. Some publications can be just to find some more details about our studies. Okay, that's all. Thank you very much for your attention.
Thank you very much, Alexei, for this inspiring talk. Can I start with my own question, which might be naive, but
yes, please. I will try to answer if I know the answer.
Yes. So of course, the important part is integration with silicon. Yes, and it's difficult to grow such big structures direct from silicon. So, and you described this procedure of, I don't know, wafer bonding to actually transfer your microdisk lasers onto the silicon. So my question is, how robust is the procedure? Is it time consuming? And the second part of it is, can you actually transfer your lasers on the finished CMOS with transistors, and would they still work, do you know?
Difficult to say, because very recently I had a talk with guys from Huawei Corporation, and just describing our results and asking what they really want, and they said that everything, direct growth of 3.5 on silicon and hybrid integration is not the final solution. So they want to have something which can emit laser light directly from silicon. So it's a dreams, and maybe it is even impossible, but everything else they consider as some, for example, epitaxial growth on silicon. It's difficult to combine processing of transistors with processing of laser. When? So first you should make transistors and then grow 3.5 or some other. In case of hybrid integration, the main disadvantage is how to say, it's a slow process. So you can use a stepper. It's a device which provides high accuracy in location of small device, as we did. So using a microscope and a stepper, you can place your device with an accuracy better than 0.5 micrometers. So you can orient your microdisk laser or some other laser in a proper position. You can integrate with, for example, waveguide and something like this. But this is an individual procedure. So you should move the first diode, the second diode, also, and so on and so on. What we did?
How long does it take? By the way?
What we did, we just transfer not the individual laser, but array of lasers. So we can simultaneously transfer some group of micro lasers onto a predetermined position, and it takes a few seconds if the operator is skilled enough. For example, my younger colleague Fedor Zubov is already skilled sufficiently, so he can did it with high reproducibility, but it's still quite tough. He has some stress, everything, when he deal with micro lasers. So it's not how to say, it's not actually mass production techniques, of course. Maybe some printing, but what is important? It's important to demonstrate that small laser with quantum dots can be placed everywhere. Silicon is just an example. You can use plastic, you can use some foil and everything. So everywhere what is required. In some cases, laser light is not required. But when it is required, you can just take a small laser, like from the how to say, you have some box where you many lasers for any cases, for any applications are just stored. So you take a proper laser, put it on the predetermined position, and everything works. So what's so important? So quantum dots are very robust against everything, against dislocations, against ambient temperature, against stress, and so on and so on. So maybe this is not the final solution, of course, and of course it is not the final solution, because people from industry thinking about scalability, about reproducibility, about money, and that's why we use very simple post growth, because simple post growth means potentially simplicity and cheapness.
Yes. Thank you very much, Alexei. Yes. So, any other questions, please?
Okay, thank you. Thank you for no questions. Okay, guys. Vladimir, thank you very much for inviting me to this conference. Very interesting for me to listen to stories about nanowires and so on, single photonics. That's I like it. I really like it. Thank you. Thank you.
Let's wait a bit. Maybe they will come up, you know, students. Don't be shy, guys. Frangos, yes.
May I ask a question about growth?
Yes, please.
You mentioned that in your quantum well dots, there are variations of thickness of the quantum wells, but also non-uniformity of the composition.
Yes.
Is there any correlation between the two? And second question, can you give a figure for the excursion in composition?
Actually, I do not have just with me some additional figures, but there is plenty of publications from my colleagues about property of this quantum well dots. They study very carefully how they grows and what's the luminescence properties and so on and so on. So this is the epitaxy is conducted in the YOF Institute by Mosavidi Group, who their first idea was to use some insertions to solar cells to provide longer wavelength absorption to gallium arsenide subcell. So, and we, together with them, considered that quantum dots have very small absorption, and it is necessary to increase absorption. And they found that if indium gallium arsenide with the composition of the average composition is roughly 40%. So it's not the conventional Stransky-Krastanov quantum dots where the composition is 50% or even pure indium arsenide is deposited. This is some intermediate case. So because quantum wells are typically requires 20 or 25%, quantum dots requires 50 or 60 or 100%. Herein, it is deposited several monolayers of indium gallium arsenide with a composition of roughly 40%. And we observe that there is some modulation of thickness. This modulation is approximately 2 times. So this means that the thinnest and the thickness is the thickest modulation parts are different in the thickness approximately 2 times. But if we observe plane view image, we see that there is some contrast, which is associated with difference in composition. So it is studied in details by Sergei Ruvimov, now unfortunately he already dead, from Notre Dame University, and he found that there is, in addition to modulation and thickness modulation, there is some modulation in composition. So this these islands have the indium content higher than average. For example, if we deposit indium gallium arsenide with a composition, average composition 40%, in the island the composition is roughly 55 or even 60%. So it's some self-organization process, like everything in quantum dots, because composition and strain are connected to each other, and if some fluctuation of composition exists, and in case of non-exact planes, there is some additional driving force, which is atomic steps associated with some angle of misorientation. So now for me, we mostly concentrate on using this sort of the active region to various applications for lasers, for micro lasers, for photodiodes, for solar cells, while guys from MSVD groups still continue study the peculiarities of epitaxial growth, of their size, composition, and so on and so on. So we are, if you are interested, I can provide you plenty of different publications about optical and structural properties of quantum well dots. Thank you.
Okay, I don't see any further questions, so let's thank Alexei again, and let's thank all the speakers for this session and of the first day of the conference. And we will start our oral session in 20 minutes, so quarter to 5. Thank you very much.
Thank you.
Sorry, I don't have a webcam on my computer. I don't have a webcam on my computer. I'm sorry. I cannot switch on my my video.
But you can share the screen?
Yes, of course, yes.
Yeah, so no problem. So in this case, I think I will just start this evening session, which is mainly composed of oral talks of young scientists, and you have 15 minutes each, including questions. So please consider time in your talks. So Hadi, I think you can start because we have many participants connected. So
okay,
and it's
so
time
please
to
just
yeah.
Yes. Do you see my presentation?
Yes.
Yes. Do you see the double screen or just the slides?
We see the double screen. Yes. Yeah.
I don't know how to do that.
But probably we don't want to see your notes, so we just want to see the.
Yeah.
Yes, like this. Yeah, it's perfect. Yes.
Okay, just.
And now you zoom in.
Doesn't work. It works.
Yeah. Excellent.
You see only one screen.
I see. Yes, we see only your slides, nothing else, which is perfect.
Okay. Okay. Very good. So, hello everyone. I'm Hadi Hijazi, a postdoctoral researcher. I'm currently working in Grenoble, France. But before my current position, I was working with Professor Dubrovsky during the COVID time, I would say, on modeling the growth of 3-5 semiconductor structures. My postdoc was funded by the Russian Science Foundation. But for today, I have chosen to present a recent paper we published about charge and spin transport over record distances in gallium arsenide metallic N-type nanowires. This study is a collaborative work between Daniel Paget from École Polytechnique in Paris and Institut Pascal, where I did my thesis in Clermont-Ferrand. So here is the outline of my presentation. I will start with a brief introduction about the experimental setup and pointer, the experimental setup used for our study. Then I will show how we passivated the surface of our nanowires before our experiment. After that, I will show the most interesting results we have obtained before concluding my talk. The sample studied throughout this presentation consists of a very long zinc blende N-type gallium arsenide nanowire grown by hydride vapor phase epitaxy HVPE at Institut Pascal. Its doping level is about 10 to 17 per cubic centimeter. Its length is about 80 micrometers and its diameter is about 220 nanometers. To investigate charge and spin transport in this nanowire, we used a polarized microphotoluminescence experiment at École Polytechnique in Paris. Here is a schematic representation of a standard spatially resolved PL experiment where we excite the nanowire or the sample with a tightly focused laser, and we monitor the luminescence of the emitted light by a CCD camera to plot the spatial profile of charge. The particularity of a polarized micro-PL experiment is the presence of quarter wave plates at the excitation and the reception, which allow respectively to excite the nanowire with a circular polarized photons and generate spin polarized electrons, two densities, spin polarized electrons with two different densities, N+ for spin up electrons and N- for spin down electrons according to these selection rules, and then collect the polarized luminescence after recombination. For example, if we excite the nanowire with a right circular polarized photon, we create an electron with spin up in the conduction band with spin up in the conduction band with a probability 3 times larger than spin down. This electron diffuses laterally inside the nanowire and until recombination with a hole to emit a circular polarized photon according to the same selection rules. Analyzing the emitted photoluminescence from the sample allows us to calculate separately N+ and N-, and then to calculate the charge density, which is the sum between these two quantities, and the spin density, which is the difference between them. The ratio between spin and charge densities and S and N gives the degree of electronic polarization. The idea behind this study is to use the spin polarized carriers to polarize localized nuclei inside the nanowire due to the hyperfine interaction between nuclei and charge carriers. The polarization state of these nuclei will subsequently be used to store information in a so-called quantum memory device. So far, we will only focus on the first step of this project and try to obtain high degree of electronic polarization and large diffusion lengths inside the nanowires in order to enhance the hyperfine coupling and to excite the maximum number of nuclei inside the nanowire. This is the experimental setup used for this study that I'm not going to explain in details, but what you have to know here is that the spectrometer coupled with a CCD camera at the reception of the setup gives us this type of spatially and energetically resolved 3D images. Now, if we do a section across the x-axis, we obtain a spectrum. Here is a 2D representation of this 3D map. If we do a cross-section along the x-axis, we can obtain a energetically resolved spectrum at a given position. And if we do a section across the y-axis, we can obtain a spatial profile with a wavelength selectivity that we use to study the transport inside the nanowire. In a structure of a high surface to volume ratio like nanowire, the surface plays an important role in the determination of transport properties. The carrier lifetime tau is reduced with respect to the bulk by the surface recombination velocity S, which becomes more efficient when the diameter decreases, the diameter of the nanowire decreases. So in order to increase this lifetime, and therefore the diffusion length, to increase this lifetime tau and therefore the diffusion length of carriers inside our nanowire, we have to decrease the surface recombination velocity. The only way to do that is to passivate the surface of the nanowire. Here we use a passivation with nitrogen due to the high stability of gallium-nitrogen bonds on the surface. It is a relatively easy process, and it should not induce any strain in the nanowire. We passivated our nanowire in the ultra-high vacuum chamber at Institut Pascal of the group Surface and Interface. We passivated at room temperature, followed by an annealing at 620 degrees C for 1 hour. This process has been demonstrated to enhance the PL emission of 2D layers. Here we see the PL spectrum of the unpassivated layer in black, and in red is after passivation. On the nanowire, this process does not induce a surface degradation, as we can see here on the high resolution TM images. And like 2D layers, the PL intensity is enhanced by several orders of magnitudes after passivation. As I mentioned before, the nanowire used for this study is grown by hydride vapor phase epitaxy and negatively doped with silicon with a high doping level, about 10 to 17 per cubic centimeters. Preliminary results obtained on this nanowire by polarized micro PL are given here for integrated PL spectrum and spatial diffusion profiles of charge in black and spin in yellow, obtained both at low temperature of 6K and an excitation power of 180 microwatt. First, the PL spectrum shows unusual structure in the near band gap emission here. Second, the spatial profiles of charge and spin shows different phases with a rapid decrease up to 2 micrometers, relatively slow one up to 12 micrometers, and again, a faster one for larger distances. For comparison, we did the same measurement on a similar nanowire, but p-doped, and instead of 3 phases, we obtained the usual exponential decay as for bulk structures. The good result here is that both spatial profiles of charge and spin extend much beyond the excitation laser profile given here in red, revealing a very good transport of charge and spin inside the nanowire up to distances of 20 micrometers. It can be concluded then that n-doped gallium arsenide nanowires exhibit remarkable and interesting properties for charge and spin transport that are worth investigating. Before giving any explanation of these results, let me show you the specific properties of our nanowire. First, this nanowire can be considered as metallic. since its doping level is 1 order of magnitude larger than the MOT insulator metal transition. Then, according to Joyev, the spin relaxation time given here is almost optimal for spin transport for the doping level we have. What's going on? I don't know what's going on. Okay. So
it's okay now, Heidi. So you can
okay,
continue.
Yes. Despite passivation, the surface recombination is still expected to be present at the surface of the nanowire, which creates a surface depletion zone of about 90 nanometer in width. This means that only a fraction of the nanowire volume remains undepleted, from which the luminescence is recorded. And the most important property of our nanowire is that it is a disordered system because of the statistical fluctuations of donors. More quantitatively, in a sphere of radius r, the donor concentration has a typical fluctuation which generates a potential delta V. So the statistical spatial fluctuations of donor concentrations give rise to spatial fluctuations in the bottom of the conduction band and the top of the valence band, as illustrated here. The mobility level shown in red. The mobility level shown in red here is the threshold above which electrons are free to diffuse. It is below the Fermi level, since the present nanowire is metallic, which means that intrinsic carriers can participate to the transport. The transport of carriers in this system proceeds either by diffusion of hot carriers above the potential fluctuations, or by hopping from between one potential well to the neighboring one. Start first with analyzing the PL spectrum near the band gap, which I recall presents unusual structure. Here I show the PL spectrum. In blue lines for only this energy range, for the charge and spin and the spin luminescence intensities. And here I show the degree of electronic polarization as function of the emission energy in the red line here. These spectra can be deconvoluted into 3 contributions. The first one is the main line M, shown here in black, centered at 1.151 electron volt. This line has a 0 polarization, suggesting that it reflects the recombination between photoholes and intrinsic electrons, which are not polarized. We have another contribution, which is the shoulder S at 1.519 electron volt, which is polarized, suggesting that polarized at 20%, suggesting that this line represents recombination between photoholes and the polarized photoelectrons that we induced inside the nanowire.
Heidi, I ask you to speed up because your time is over actually.
Yes, okay. There is also a third line at higher energy, also polarized at 20%, which suggests that it represents a combination between photoholes and hot polarized photoelectrons. These attributions are confirmed by the dependence of each line on the excitation power. If the slope is 1, it means that you have a monomolecular regime and a recombination between photoholes and intrinsic electrons. On the other hand, if the slope is 2. This means that we have a bimolecular regime and a recombination between photoelectrons and photoholes. As you can see here, the line M is very well described by a monomolecular regime, while line S and line H are described by a bimolecular regime. Let's now analyze the spatial profiles. Here I show the charge spatial profiles for lines M and H in blue and black lines for different excitation powers. The presence of the tail that extends to distances larger than 20 micrometers reveals that we have a good diffusion of photoelectrons at large distance. But luminescence at large distance means a recombination with a hole at that distance, which usually do not diffuse as far due to their large effective mass. In order to understand that, we plot two ratios, B and C. And calculated from the spatial profiles of lines M and H. Line C reflects the concentration of photoelectrons N, while B reflects the ratio between photoelectrons N and photoholes P. From the profiles of these two ratios, in red and green, we can calculate N and P at any distance. And using the charge neutrality, we can deduce the intrinsic electron distribution. Finally, we obtain these profiles for different carriers densities. The main result is that we obtain a redistribution of the intrinsic electron density along the nanowire, which creates an internal electric field that helps holes to diffuse at large distances and recombine with photoelectrons. To study the spin transport, the polarization of the photoemitted luminescence is recorded for lines S and H at different distances from the excitation spot. The high values of the polarization reveals that spin is also transported over large distances as charge. As conclusion, we obtain charge diffusion over record distance as large as 20 micrometer. This is due to the build-up of an internal electric field generated by the redistribution of Fermi C inside the nanowire. And finally, we have seen also that the spin is transported to these large distances. I would like to thank you all for your attention and the sponsors of this work and the Russian Science Foundation as well. So
thank you, Hadi. Are there any questions in the audience?
Go back to the first slide.
So Hadi, maybe you can explain why your silicon-doped nanowires are N-type, while usually in MBE we see the opposite. I mean, I know the answer, but it's new for many people here.
Yes, yes. Actually, we have demonstrated this effect in in a previous paper. We have discussed why in MBE we obtain a p-type doping with silicon in gallium arsenide, while in HGPE we obtain always a N-type doping. And we related this to the arsenic to gallium ratio in the catalyst droplet during the growth. In MBE, we have a very low arsenic to gallium ratio, while in HGPE, we are supposed to have a larger arsenic to gallium ratio. And this helps the silicon atoms to be incorporated more easily on gallium sites in HGPE and only on arsenic sites in MBE. This explains the difference in behavior between these two techniques.
Thank you, Hadi. I have to say that we should move on, so thank you very much.
Thank you.
So the next presentation is by Mohammed Zahawan, and it's on the improvement of the tin incorporation into germanium tin nanowires. And Hadi, as far as I understand, it's going to be a recorded video, yes?
Exactly. I will share a video that
So
Mohammed gave me.
you take care of them?
Yes,
of this
of course,
then?
of course,
Because,
yes.
yeah, just to show us the video, yeah.
So here it is. Do you see it?
Yes.
Okay. I can start if you want.
Yes, please. Yes, of course.
Okay.
Good morning to all. I'm going to present you the vapor liquid solid growth of germanium tin nanowires, and especially how we can improve the tin incorporation in these nanowires by varying the liquid phase composition. So all this work was done in LTM lab in collaboration with CEA. So the question that maybe you can ask, why germanium tin? So you know that germanium has an indirect band gap, as we can see here, and by incorporating this metallic tin in the germanium lattice, we can switch the germanium band gap from indirect to direct, as we can see here and predicted by several calculations, and they show that the transition can occur with typical values of tin ranging from 6 to 11%. And this is important for different micro and optoelectronic applications like lasers, tunnel FETs, and MOSFETs. However, the epitaxial growth of germanium tin layers remains very challenging due to the low solubility of tin, which is lower than 1%, the large lattice mismatch, and this leads to high tin segregation, surface roughness, and also strain. And maybe you know that the nanowire geometry is a solution to overcome this kind of limitations. So thanks to the stress relaxation on the lateral free surfaces of the nanowire, we can grow high quality germanium tin material with high tin concentration on low cost substrates like silicon, for example, and without any phase separation. Their high aspect ratio can also be important for optoelectronic, for light absorption and emission, and also can be adaptable for flexible system, which can improve the performance of devices. There are different ways to grow nanowires, but the most common method is the vapor liquid solid process. So it is very simple. We start with a metallic liquid droplet, in most cases gold, and then from the vapor phase, the elements of the material that we want to grow incorporate in the liquid phase until supersaturation. In this case, the droplets try to minimize the total energy and to return to equilibrium states by the crystallization of the excess of the elements as the interface here with the substrate. And then we have the nanowires. This is why it is important to control and understand the liquid phase composition to control the solid composition. So if we look to the state of the art, we can find different papers dealing with germanium tin nanowires grown by the vapor liquid solid process with gold catalyst. Of course, they can reach high tin contents in these nanowires. However, the precursors used in that process remains complex for the industry and also for doping. But if we look to these selected papers, the authors show that adding different fractions of silver in gold catalyst can improve the incorporation of tin in the solid nanowire, as we can see here and here. And this was explained by what we called the solute trapping mechanism, which means that the amount of tin incorporation can easily be increased by a faster growth rate. And this is why we are interested to study the impact of adding different elements in the gold catalyst on the tin incorporation in nanowires. In our lab, we have an industrial and hot wall low pressure chemical vapor deposition. So for germanium tin growth, we use German, which is a low cost precursor for germanium source, and tin chloride for tin source. And we added some hydrogen chloride in the vapor phase to improve the morphology of nanowires and suppress any tapering. So these droplets were obtained by evaporating thin gold film following a dewetting step at high temperature. And as demonstrated in the previous papers, the tin incorporation is improved at low growth temperature and high growth rates. This is why it is important to fix carefully this growth parameter. To study the impact of the growth temperature, we fixed all parameters and we varied only the growth temperature from 300 to 450, as shown here from these SEM images. The substrate here is germanium 111. We can see that the nanowire growth along the 111 direction. We can see also a noticeable change of the morphology and the growth rates of nanowires, and this is due to the variation of growth kinetics of absorption, diffusion, desorption, and also crystallization, which are thermally activated. The maximum growth rate is obtained at 400. Now we have to do some characterization to estimate the variation of tin incorporation with this growth temperature variation. So we did nano-OG spectroscopy on dispersed nanowires. In fact, we can estimate the tin and concentration on the surface and also in depth by etching with anion argon, as explained here. Here I show you an example of the profile of germanium tin nanowire grown at 400 degrees C. We can see that we have a very high thin concentration at the surface and then decreases in depth to stabilize at around 2% in nanowire core. This was also confirmed by the radial EDS mapping after a FIB preparation, as we can see here, and we can see that we have this core shell-like structure, a very high thin concentration at the surface here. Overall, we have a low tin incorporation in nanowire core, whatever the growth temperature, and the maximum was at 400 and for 2%. Now we fix the growth temperature at 400 degrees C and we add different fractions of silver, aluminum, gallium, as we show here. A sample with the presence of silicon and the gold droplets was also prepared on silicon 111 substrate, because silicon atoms can be transferred from the substrate to the droplets during the high temperature annealing ramp. In fact, by adding these foreign elements, thermodynamics and growth kinetics are impacted, and this explains this change in the growth rates and especially with high fractions. We did nano-OG depth profile on nanowires grown with high fractions of foreign elements as shown here. And surprisingly, these elements improve the homogeneity in the nanowire depth, suppressing this core shell structure. And this can be due to a better mixture of the liquid phase. And also the average tin concentration in the nanowire core is improved, and especially with aluminum reaching 9%. And suppose that we have a germanium tin material with a direct band gap. In collaboration with ITMO University, we proposed a theoretical model to explain these results in a qualitative way. So in fact, the tin fraction can be expressed by the ratio of its growth rates on the total growth rates, which means the growth rates of tin and germanium. And the growth rate depends on kinetics of diffusion and crystallization in the liquid phase, and thermodynamics, which represents the difference in the chemical potential between the liquid and the solid phases, delta mu. So if delta mu is equal to 0, we have this equilibrium. But higher than 0, we have this deposition or crystallization. And this is the expression of the chemical potential of the liquid phase of the elements. And because it is more complex to estimate growth kinetics parameters, we limit our model to a thermodynamic approach, considering that the tin incorporation depends on the minimization of the total free energy of the system. So we assume that a monolayer starts by forming a pure germanium nucleus. This latter extends by collecting germanium from the liquid until the incorporation of one atom, which becomes energetically preferable. In the case of pure gold, the free energy of both germanium and tin can be expressed following these equations. And if we plot as a function of temperature at different tin concentrations in the liquid droplets, we can obtain these curves. So we can see that we have a good correlation with experimental data, and tin incorporation remains low in such condition. And now we plot by adding different foreign elements in these equations, we obtain these curves. We can see that compared to pure gold, here adding fractions of foreign elements can improve the tin incorporation. So it is important to note that it's a qualitative model, but it shows the important effects of thermodynamics to explain the experimental results. To conclude this study, we have shown that we can grow germanium tin nanowires with a low-cost industrial process. And by adding different fractions of selected elements in the gold droplets, we can improve the incorporation and the homogeneity of tin inside the nanowires. And then we have proposed a thermodynamic model based on free energy minimization and shows a good correlation with the experimental data. Overall, these results can be used for tuning the composition of a large choice of semiconductors nanowires by adding suitable foreign atoms to the catalyst droplets. And thank you for your attention.
Okay, so thank you, Mohammed. I don't think we are supposed to put any questions here in the case of pre-recorded video, so we just move on. So the next talk will be given by Yuri Bernikov with the title Modeling the Multi-Alloy-Driven Selective Area Growth of Indium Phosphide Nano Insertions Integrated into Silica. Yuri, please.
Yeah, thank you. Can you hear me clearly?
Yeah.
Okay, so I start the sharing my screen, and okay, you can see the presentation now, don't you? Yep. Yeah, this is a presentation, is it?
Yeah,
Hello?
we can see it. Okay, you can just start.
Okay, great. The work is actually done in different places. So the growth was done in Denmark, in Technical University of Denmark. And there's DTU Photonic and DTU Nano Lab, which is also responsible for TEM characterization. And the modeling and the optical measurements, they are done in St. Petersburg here. Actually, what is the work of, what's the motivation of the work? Currently, there are several ideas how to integrate 3-5 materials with silicon, and that's mainly wafer bonding, which is quite developed technology today. There are also several attempts on template-assisted growth when you create a pattern by lithography on the surface, on the silicon surface, and then fill it with the epitaxially grown 3-5 material. Another approach which we heard a lot today, that's the nanowire growth, and well, I probably shouldn't comment that part more. So if we talking about direct growth on silicon, direct growth of 3-5 materials, there are two main problems with those structures. First problem is the lattice mismatch, which leads to thread dislocations in the structures directly grown in silicon, which I can see here, for example. Another problem is the antiphase boundaries, which is caused by the polynucleation of the 3,5 structure. And so, well, you get this antiphase boundary in the plane where these two nuclei meet together. So ideally, what you need to integrate 3,5 material into silicon is first get rid of misfit dislocations. So for this, you need some effective stress relaxation. And the second, you need to make sure that you have only one nuclei for one crystal, one structure. As you heard several times today, you can grow nanowires, and that would be one of the possible problem solution. But here I would like to suggest another idea which also works here. So the method we suggest is it's based on the selective area group. First, what you do, you take the substrate. In our case, it was silicon 001 substrate. It was covered by silicon nitride mask, amorphous mask. Then the holes were etched by combination of dry and wet etching. Next, these holes inside the silicon substrate were filled with the indium melt. Then this melt was annealed under the crystallization under the group 5 precursor flux, which in our case is phosphine. So as I see, this method combines two different approaches. First, that's the selective area growth. So you define the exactly where the structure should be. And second, you control the nucleation in a way similar to nanowire VLS growth. We just heard in a couple of previous talks. So here you ensure that you get only one nucleus in your melt if the melt is small enough. What kind of structure you can obtain in this case depend on whether you optimize or non-optimize the growth conditions. First, if you introduce no annealing, if you just deposit the indium melts under the phosphine flux, what you see, you get the whole the whole hole in the silicon substrate filled with the indium, and almost no phosphorus can be traced inside. Then, after annealing under intermediate flux, what you can get the indium phosphide nucleated in one of the on one of the walls. But still, most of the hole is filled with their pure indium. Only some indium phosphide can be observed on the wall. Finally, further increase of the annealing flux led to filling of the whole non-insertion with the indium phosphides with their indium and phosphorus concentration close to 50%. So that's if you further increase the annealing flux, you get very similar results. So in this case, you just need to reach the some threshold value for the annealing flux. Next is what's the impact has the growth temperature or the substrate temperature. From just first glance, there is some optimal temperature where you get the better crystallinity and least amount of the defects. So there I will explain what's the origin of these defects and how to avoid that, and what's the why you get this optimal temperature. So what can get wrong when you anneal and crystalline the indium melts is that indium phosphide can nucleate on the side wall, on the wall of the insertion, and then during the crystallization cover the top of the hole faster than absorb enough phosphorus material to crystallize all indium in the volume. So what happens in this case? In this case, the indium phosphide blocks the way for phosphorus precursors to and actually stops the crystallization of indium phosphide. So as a result, you get residual indium inside the hole, which leads to plenty of crystal defects. So how to control that? We describe the number of residual indium atoms as the initial number of indium atoms, minus the number of phosphorus atoms which were absorbed before the nucleation of indium phosphide, and then after nucleation during the crystallization process. You can also absorb and desorb some phosphorus atoms. So for all these processes of absorption and desorption of phosphorus, and actually for the some equilibrium phosphorus concentration during the annealing before the nucleation, different temperature dependencies can be found and grouped into two different exponential factors. First, the Grove exponential factor, which describes the phosphorus concentration before the nucleation of indium phosphide. So that's this term also includes the phosphorus atoms adsorbed after the nucleation as well. And you also should include the phosphorus desorption during the nucleation. So in this case, what you get the competition between the absorption of the phosphorus and the rate of phosphorus absorption and the rate of covering the top surface of the hole. If the covering of the top surface of the hole is faster, you get some residual indium. If not, if you get enough phosphorus to nucleate to nucleate and crystallize all the indium phosphide, it means that you can eliminate the residual indium in the non-insertion. So what does it mean in terms of optical properties? Is in this slide, actually for all of these three optimal and non-optimal temperatures, we can see some PL signal at room temperature and much higher intensity of PL signal at nitrogen temperature. But as we see in optimized structures where almost no residual indium is observed, we see a much higher intensity of the photoluminescence signal both at room and nitrogen temperature. In non-optimal in non-optimal samples with their non-optimal Grove temperature, what we typically observe some residual indium at the bottom, which is also which is always accompanied with their plenty of crystal defects inside the indium phosphide non-insertion. In case of optimal Grove temperature, most of the structures indium free, and defect-free. When I say defect-free, I say that we observe no dislocations, but we still can see the lattice twinning inside the indium phosphide. So what's the role of this lattice twinning in terms of optical properties? Is so-called type 2 band alignment. When you see when you get the band gap narrowing due to neighboring of zinc blend and word-side insertions. In our case, we actually see no signal from word-side, but this frequent twinning could be interpreted as the small insertions of word-side phases, which leads to a small shift in the photoluminescence energies. So actually inside the peak we observe where there we see two peaks, which is for pure zinc blend phase and for type 2 alignment due to this twinning effects. So a few conclusions here. First, this droplet-driven method for selective area epitaxy actually works and provides nice sharp interfaces between indium phosphide and silicon. And well, the only defects we see is there are some twinning defects, which are leads to slight widening of the PL or signal, which is it can be interpreted as a pure zinc blend and to type 2 alignment in the band structure. And so under non-optimal conditions, we can see residual indium, which deteriorate in the crystal quality and the PL signal. But this remaining indium, residual indium, can be eliminated by choosing the proper temperature of the substrate during the growth. So here I'd like to thank you for your attention. But before that, a couple of ideas. What we're going to do next is we want to choose different hole shapes, and also we are planning to introduce some indium arsenide wells here inside to tune the luminescent properties. So here, thank you, and I would be glad to answer your questions.
Thank you, Yuri. It's a very interesting talk. So my minor question regards this exponential dependence for the residual indium, I think.
Mm-hmm.
So do you know the parameters entering these dependencies, or they're just fitting parameters?
No, those parameters, it's actually impossible to know them exactly, because behind this curve, what we get one assumption that the number of residual indium, indium atoms is proportional to XRD signal, which we actually fit. So, but the proportionality, the coefficient of proportionality is there.
Yeah. How many unknown parameters or fitting parameters do you have to fit the 3 data points then?
So there's 3 parameters, I0, I1, and I2. That's the pre-exponential factors.
And for this,
that's the minimum parameters we can, in general, could have here.
TD, is it known?
TD, yes, it's known from the literature.
Mm-hmm. I see. Thanks. Any other questions? Yes, Alexei, yes.
Yuri, thank you for the interesting talk. Could you please explain a little bit more? You said about different shapes which you are going to try next, but why these shapes? Why the shapes are have high aspect ratio? So they are rather deep than wide. Probably if the holes will be shallow, more Indy will convert to Indy pair in your process.
Well, yeah, but sir, that's another problem here, because what you can do, you can start with the slightly filled, not completely filled, but slightly filled on the hole. So you get only this part filled with indium, then you crystallize it with the phosphine, for example. Then what you do, you continue growing and deposit more indium phosphide and indium phosphide arsenide on top of it. So that's not a problem. Why to have different shapes? Just to experiment with their different structures you could get here.
Thank you.
And of course, that's a open question. What's the strain relaxation will be there? So far, we see that we get a nice crystalline quality.
Any other questions? If not, let's thank Yuri again. Thanks. So the next talk will be given by Vladislav Grichin, and it's entitled Plasma-Assisted MBE Growth of In-Gun Core Shell Nanowires on Silicon Substrates.
Hello.
Hi.
Yep. Hello. Thank you, Dr. Vladimir Dubrovsky, for the opportunity to participate in this conference. My name is Vladislav Grichin. I'm a PhD student of Alfred University. Today I'm going to talk about plasma-assisted molecular beam growth of indium-gallium core shell nanowires on silicon substrate. I will start with the fundamental properties of indium-gallium nitride ternary compounds, main challenges and approach to overcome them. Next, I will talk about the experimental part of this work. Finally, I will analyze structural and optical properties of ground samples. As it was mentioned before, indium-gallium nitride ternary compounds are direct band gap materials at any indium molar fraction. A band gap energy of indium-gallium nitride can be tuned from 0.7 to 3.43 electron volt by changing indium molar fraction. In this regards, indium-gallium nitride are particularly attractive for solid-state lighting and renewable energy sources. However, latest mismatches between indium nitride and gallium nitride is huge and consists of about 11%. Consequently, indium-gallium nitride has two critical challenges. The first is the wide miscibility gap as shown in the figure on the right. The second, and small additions of gallium or indium into a ternary compound changes its lattice constant significantly, and indium-gallium nitride grown on underlying binary substrate become highly strained. On that account, significant difficulties arise in the growth of indium-gallium nitride with high indium content and high crystal quality. Mainly for these reasons, maximum internal quantum and external quantum efficiency of commercial nitride-based LEDs in the green to red visible spectrum is very low. One of the approaches to overcome these challenges is a nanowire growth. In addition to well-known advantages of nanowires, they can be used to calculate the miscibility gap of ternary compounds. This was shown on nanowires grown by vapor phase epitaxy, the results of which presented on this page. However, there are practically no data on the direct growth of indium gallium nitride nanowires on silicon by plasma-assisted molecular beam epitaxy. The aim of my talk today is to consider the influence of the substrate temperature on the physical properties of InGaN nanowires grow by PA&B. This page demonstrates the used equipment and the growth diagram. The work experiments were performed under nitrogen-rich growth conditions with equal to each other gallium and indium fluxes at substrate temperatures of from 655 to 665 degrees. It should be noted that the growth process started with simultaneous opening of gallium and indium sources and without deliberate formation of core shell heterostructure. Let's consider some morphological properties of grown samples. The table below demonstrates the morphological parameter of grown samples. Sample A was grown at substrate temperature of 665 degrees, and the sample consists from coalesced nanostructures. Sample B was grown at 660 degrees, and the sample consists of partly coalesced nanowires. And sample C was grown at 655 degrees, and the sample exhibits complete separate nanowires. Let's consider structural properties of sample A obtained by TEM measurements. On this page, we can see the TEM image of the nanostructural sample A, gallium distribution in the nanowire, indium distribution in the nanowire. Just a second. And the EDC spectrum of the upper part of nanowire sample A. As can be seen from the figure, gallium is practically homogeneously distributed in the nanowire, whereas the indium gradually increased from bottom to top of nanowire, and the indium content in the upper part of nanowire is about 10%. Similar measurements were performed for sample B and sample C. Here we can see the TEM results of sample C. As can be seen from the indium distribution, the indium is localized at the central part of this separated nanowire that indicates a spontaneously formed core shell heterostructure. It is interesting to note that the indium content in the core of nanowire is about 35%, and in the shell is about 4%. Also, sample B has a similar core shell heterostructure, but the indium content is about 30%. All samples demonstrate intensive photoluminescence at room temperature. The photoluminescence maxima are in a good agreement with TEM results. Also, taking into account TEM results, the low intensive band of sample B and sample C is due to the nanowire shells, and the photoluminescence maxima of sample B and sample C in green to yellow spectrum is due to nanowire cores. We compared our data with literature. This figure on the right shows a black curve plotted in accordance with Vegas law. Multicolor signals is our result, and black signals is data obtained from different research groups. Our results are in a good agreement with the Vega law with the Bowen parameter of 1.43 electron volt and data obtained by different research group. So this page illustrates the main conclusions of the work. The morphology and chemical composition of indium gallium nitride nanowires can be tuned over a wide range by only a slight change in the growth temperature. The optical bandgap energies of the ground samples are in a good agreement with Vegas law at Bowen parameter 1.43 electron volt, and literature. The results of the growth of indium gallium nanowires with blue, red, and yellow photoemissions can be used for creation multicolor micro LEDs. Thank you for your attention. I'm ready to answer your questions.
Thank you, Vladislav. So, are there any questions? Okay, I have a question then. So you observe in your results the spontaneous formation of core shell structure in GaN nanowires. And I think the same thing has been seen in InGaNs grown by VLS process.
Yeah.
So do you see any similarity here? I mean, is it due to the fact that indium is probably more diffusive, so it incorporates faster from the top, and then gallium forms the shell, or something like that?
I think in case of indium gallium nitride nanowire growth, the growth mechanism of without droplets, and
yeah, I know, but still you have the top, which may have maybe lower chemical potential compared to sidewalls, so there is a surface diffusion along the sidewalls to the top. This has been described for nitrides, I mean nitride nanowires.
So maybe between indium gallium arsenicum and gallium nitride nanowires can similar mechanism. So I think.
So you don't know the mechanism of this core shell formation?
Oh no, we now working on
I see.
this problem.
Thanks.
May I have a related question? How reproducible is this spontaneous formation? Can you control it? Can you make it stronger or weaker?
We can control it in the narrow range from indium content about 30% to 50%. So next, this core shell structure is decomposed.
Okay, thank you.
Okay, so I think we have to move on. So let's thank the speaker again.
Thank you.
Yeah, so the next talk is, I think, should be given by Vladimir Neplov, if I'm not mistaken. Hi. Where is? Yeah, hello. Yeah. So you will be talking about flexible devices. So I won't list all of them. So please start. Yeah.
Okay. So can you see the slides?
Yes.
Yes, thanks. You can start.
Okay, so I work with Ivan Mukin in Alfred University, and my presentation is a logical continuation of Maria's Chernysheva presentation and her work, because I was a PhD student of her. And here I will present you about LED membranes based on 3,5 nanowires and perovskite gallium phosphide hybrid nanowire LEDs, and also about R and UV to visible range converters and silicon-based second harmonic generators. So the group which I present, because this work is a result of the team of flexible devices in our laboratory, and outline follows the photo. So Fedor is the main person of gallium phosphide arsenide gallium phosphide nanowire red LED, and in Gangan multi microwire blue LED. Maria Baeva is responsible for perovskite works, mainly the green LED device and UV and IR to visible converters based on perovskite quantum dots in non-woven mats. Victoria is the person who worked on silicon nanowire third harmonic generators. And the perspectives I gave you are delivered by Anna Miroshnichenko with her development of functional PDMSs and basic PDMSs for nanowire PDMS membranes. And the student Sungat Mohangalia developing the patent single-wall carbon nanotube pixel array electrodes. So let's start with gallium phosphide arsenide nanowires. These are the SEM images. I don't know if you can see the pointer. Is it visible? Okay. These two SEM images are the gallium phosphide nanowires, which are approximately 5 micrometer, 3-5 micrometer high. They have axial structure with gallium phosphide arsenide active region, and they were grown on silicon substrate. Then we encapsulate them with our G-coating method to the PDMS matrix and release it from the substrate by pilling. Then we put single-wall carbon nanotubes contact pads, reverse the structure, put it on the back side, and then you can see the device structure in the left bottom corner, the photo of it. So the results are given on the right part of the slides. You can see the PL intensity results, PL spectrum, and with the main line on 650 nanometers. And then you can see that the IV curve is in the upper right corner. Here we see a relatively high opening voltage of 7.5 volt or 7 volt. It is due to the Schottky barriers, which are presented in the carbon nanotube nanowire interface. And the EL intensity is very noisy, because when we measured it, unfortunately, the device was almost dead, but the photo captured was done when it was still very good function. This work is published in the paper cited in the left side. So next results are about stretchable Ingangan microwire blue LED. It basically follows Maria's research, because we use the same microwire from Grenoble, MOVPE, but originality in this work is the stretchable contacts. Because we use single-wall carbon nanotube films, we can make stretchable contacts out of them. by pre-stretching the whole structure and then applying the contacts. In this case, after releasing the membrane, the contact parts can survive repeatable stretching in the given line. So if the PDMS membrane was pre-stretched to 20%, it means that it can re-stretched for these 20%. And in the right part of the slide, you can see the results of stretching cycles and the voltage which are required to eliminate the nanowires. And we can see that in relaxed state, we see almost no degradation of the structure, while in the stretched regime, it is 10% or 15% of decay in the conductivity of the substrate. This structure is semi-transparent. We measured 43% transparency due to the carbon nanotube film not fully transparent, but we can relatively easily improve it up to 65%. And that means that we can make stacking of membranes of different colors. For example, with the previous slide, with the red nanowire membrane, to form a multicolored device. So the next device is a hybrid cesium brom 3 with polyethylene oxide active material, which eliminating green range. And we formed it onto the nanowire array encapsulated into PDMS. The whole structure was released from the substrate, and again, for both sides, carbon nanotubes were applied. And the structure illuminate in the area where the nanowires protrude the perovskite region. And in this case, we have a sophisticated contact and a semi-transparent structure, so it can be integrated with other membranes and other flexible devices by direct putting them on top. The next work is about photonics, and here we can see that quantum dots, perovskite quantum dots, based on halide perovskite, they are very efficient. They have about 95% and higher quantum efficiency, and that means that they can effectively convert ultraviolet light into the visible range. Here you can see how colloidal particles illuminate in the left side of the slide. And after we dissoluted in the butyl acetate DMF mixture, we have precursors, basically cesium bromium and plumbum bromium 2. And then we put this mixture into the fluoropolymer, and using electrospinning method, formatted non-woven mats containing perovskite material. And because of conditions of this synthesis, perovskite material reassembled into quantum dots. And here you can see the proof. We made TEM measurements and XRD measurements showing the perovskite phase formation. And the size of this perovskite material clusters is approximately 10 nanometers. So they have basically the same size as quantum dots, original quantum dots. And the photoluminescence line is relatively broader than the initial nanoparticles. But we associated with the distribution of the sizes of the quantum dots inside the non-woven mats. This structure also effectively converts infrared light into visible light because of 2-photon absorption and luminescence. We also developed a method to encapsulate and peeling encapsulation and peeling of silicon nanowires. Here on the left side, you can see the processing, the formation process of silicon nanowire array. It is a top-bottom approach by inductive coupled plasma etching and using microsphere mask. We can make a very nice looking array of almost homogeneous size silicon nanowires. Then we repeat the approach, encapsulation, release, and then we investigated the third harmonic generated inside the silicon material. As you might know, silicon materials have no second harmonic generation in volume because of the symmetry of the silicon crystal, but the surface of it has a second harmonic generation, and that's what we developed in the not published yet work about silicon mesoporous spheres. These spheres formed in the Yoffe Institute by the liquid methods, and during the formation of silicon spheres, the structure of it is very porous. So basically, these spheres consist of very thin surface of silicon, and that's why we observed a strong second harmonic generation from silicon, which is interesting from fundamental point of view. So this research is based on integration of electronics based on silicon and photonics. So the perspectives are given by further exploit of the design we proposed, the PDMS nanowire membrane, which can be 3-5 nanowires or silicon nanowires, and perovskite materials, because we can substitute bromium with iode or chlorium, and in this case we can cover all visible range, so making devices illuminating in red, green, in red, blue, or in the range between red and blue, so for covering the whole spectrum. Also, we can cover it with methyl ammonium plumbium iode-3 to make a solar cell device. In this case, also interesting work we do now is developing of silicon nanowires with heterostructure. So the final device would have a tandem solar cell. Silicon nanowires with heterostructure will absorb the infrared region, while the perovskite material will absorb in the shorter wavelength region. So another thing, it's tomorrow presentation by Anna Miroshnichenko, is development of functional and improved properties PDMSs. Here you can see the published results. It's about improving of silicon strength by adding styrene complexes. And also interesting research is dedicated to the luminescent polymers with europium, terbium, thulium, lanthanide, bipyridine PDMSs, and also the conductive silicones with ferrosanil containing complexes. In this case, about the ferrosanil conductive silicones, we published a paper with the contacts based on them. So the last thing I want to share with you is about development of patterned silicon wall, single wall carbon nanotube films, which we use to make electrode. Maria mentioned it in her presentation. It's an electrode with many pixels with addressing contact tracks, which are strain insensitive. And in this case, we can address areas of membranes and illuminate them separately, and making a full color device if we combine whole all three color channels based on different materials. So basically that's it. Thank you for your attention. I'm happy to answer any question you have.
Yeah, may I have a question?
Thank you. Yes, of course. I expected a question from you.
For the last slide, number 10, about these zigzag contacts here. Have you tested their stretchability? So how good they are?
Yes, we tested it. Actually, I thought about putting it here, but thought no one will ask this question. Yes, it's with this pattern, as you can see on the photo on the right side, it's strain insensitive. It's truly so. But there are another patterns which are more like a loop. You know, in this case, it's stretchable in all directions, not only in the horizontal, in the aligned with the direction of the stripe, but also in other direction. And yes, it works.
Okay, thank you. But in this particular case, it's metal, or it's what is the material of the contact?
It's fully carbon nanotubes.
So you just okay. So
yes.
it's all carbon nanotube. Okay.
Yep.
But then it's difficult to scale it to micrometers, no?
No problem. It's done by photolithography. So we make a mask, and we can make tens of square centimeter size contacts like this. It's not a problem at all.
Looks good.
Yes, I agree. It looks very good. Thank you very much again, Vladimir. And the next talk will be given by Igor Ilkiv, and it's entitled MBE growth of hexagonal germanium on Algas nanowires. Please, Igor. Yeah.
Good evening. I'm very grateful for the opportunity to present our results. Present work is devoted to the study of growth process of hexagonal germanium on the Fe-B5 nanowires. This is the outline of my work. Firstly, I will discuss why hexagonal germanium is of interesting. Then we will talk about experiments, and we will finish with result and discussion. It's well known that diamond cubic germanium is have an indirect band gap. In turn, it was predicted that the hexagonal 2H germanium may have a direct band gap. That's why this materials is of significant interest from the fundamental point and from the creation of different applications, such as light emitting diodes that are compatible with traditional CMOS technology. One of the problems in ways to obtain hexagonal germanium is epitaxy using the templates. In this connection, semiconductors Fe-B5 nanowires with pure wurtzite crystal structure is ideal candidates for this. And recently, the growth of silicon on the gallium phosphide and germanium on gallium arsenide nanowires and luminescence from such structures was achieved. In our work, we decided to use the hour growth approach, both synthesis of nanowires and grow germanium, and the deposition of germanium was conducted using molecular beam epitaxy. In detail, we used a reverse tap, that was equipped with the sources for grow Fe-B5 materials and the electron beam sources for deposition of silicon and germanium. We started with the growth of wurtzite gallium arsenide, and after the nanowire formation, the temperature was decreased below the static point for germanium and gold, and the deposition of germanium was conducted. On the typical gallium arsenide nanowire ensemble is presented on the slide. As you can see, despite the great efforts made to grow pure wurtzite nanowires, nanowires consist of thin blend and wurtzite segments. Nevertheless, long wurtzite segments are present. As it can be seen, the deposition of germanium led to the formation of thin, about 3-5 nanometers germanium layer. Elementum analysis of nanowires revealed that it was a conformal, that germanium was distributed uniformly. In order to improve crystal quality, we decided to use aluminium gallium arsenide nanowires. It is known that such nanowires have near pure wurtzite crystal structure, and both aluminium gallium arsenide and gallium arsenide are lattice matched with the germanium. The samples obtained are presented on the slide. As can be seen, the deposition of germanium led to the formation of nanowires with smooth side walls and with the bulbs on the nanowire tops. Raman spectroscopy revealed the formation both cubic and hexagonal phase of germanium, as it was demonstrated after the germanium bulb has a cubic crystal structure, while the sidewall shell have a wurtzite crystal structure. High resolution study revealed that germanium shell has a pure 2H crystal structure, and this layer was not strained. Detailed investigation of single nanowires by EDX spectroscopy revealed that germanium was not distributed uniformly. Combined image allowed us to make a conclusion that germanium formed stripes. To understand why germanium form a stripe along the side facet of aluminium gallium arsenide nanowires, we consider the model. It takes into account the surface energy change upon the forming of rectangle stripe. According to this model, germanium stripes are formed because the germanium atoms do not wet the side facet of nanowire due to a high interface energy between these two materials compared to wurtzite gallium arsenide. This conclusion was also supported by the fact that germanium forms uniform shells if grow on pure gallium arsenide nanowires. It is a conclusion. Hexagonal 2H germanium structures with tunable geometry can be achieved using appropriate nanowire isotop plates. For future steps, of course, it is we have to demonstrate the photoluminescence from such structures, and we want to obtain structures with multi-shells with quantum wells of germanium, and we also want to use gallium nitride and indium arsenide nanowires as interplates, because gallium nitride, if we use gallium nitride nanowires, we have a problem with crystal quality. And for indium arsenide nanowires, the main features of this structure that they have a pure word-side crystal structure, and they have a diameter of about 10 nanometers. That's all.
Thank you, Igor. Are there any questions? Okay, so may I ask you, I mean, 2H germanium covering uniform with the nanowire sidewalls has been demonstrated before, as you know, in the work of Eric Beckers, for instance, and his group. So do you think that maybe the main result here is that germanium forms stripes rather than, you know, the shell structure? Is it interesting, or can it be potentially interesting for some applications, do you think?
Yes, such structures can be used as a quantum wires.
Quantum wire, yeah.
Yes,
exactly, yeah. Any more questions from the audience? I don't see any, so let's thank Igor again. So the next talk will be given by Artem Tarasov, and it's about sublattice ferromagnetism in quasi-freestanding graphene. Yes, please.
Good evening, everyone. Can all see my screen?
No, because I think Igor has to switch off his presentation before you can share the screen. Igor.
Okay.
Yes. Yes, it's okay now. We can see it. Okay, we can hear you. Okay, so you can just start.
Okay. Good evening again. My name is Artem Tarasov, and I am a PhD student of St. Petersburg State University. Today, my presentation will be devoted to realization of a ferromagnetic state in quasi-freestanding graphene and its possible application in photonics. Let's start by looking at main features of graphene. As many of you probably know, graphene is a single layer of carbon atoms arranged in two-dimensional conic-amp lattice. Its atomic structure determines the hexagonal form of its parent zone with two opposite K points. The main feature of graphene is the presence of a Dirac cone in its electronic structure. This feature implies a linear dispersion near the K point and high mobility of charge carriers. Meanwhile, even though the Dirac cone is a very interesting feature of graphene, there is a significant problem of its use in electronics, spintronics, or electronics, due to the fact that graphene in its quasi-freestanding state is a gapless and non-magnetic material with weak spin-orbit interaction. However, thanks to the proximity effect created by the contact of graphene with a magnetic substrate, it is theoretically possible to create three variants of magnetic ordering in graphene: antiferromagnetic, ferrimagnetic, and ferromagnetic. It is worth explaining that ferromagnetic ordering differs from antiferromagnetic one in the sense that graphene sublattices have magnetic moments different not only in the direction, but also in their values. Today, I will talk to you about the first example of implementing graphene ferromagnetic state in real atomic structure. And I try to demonstrate its convincing prospects for application in photonics. Before returning to graphene again, I would like to say a few words about the electronics in two-dimensional materials. In semiconductors electronic structure, we have two extrema formed by highest valence band and lowest conduction band. These extrema called valleys. And the electron's position in one of these valleys represents an additional valley degree of freedom for the electron. The main objective of electronics is finding the way to use the electron's valley degree of freedom to encode and process information, as well as it is applied for electron charge in electronics or for spin of electron spin in spintronics. In order to address to a valley pseudospin, we can use circular polarized light and inject exciton into one valley. Then this valley polarization can be experimentally read out by measuring the circular polarized components of emitted photoluminescence intensity. If a two-dimensional system has an antiferromagnetic ordering, its Hamiltonian includes the Coulomb interaction of opposite spins on the same atomic sites. And in such system, we have a new coupled spin valley degree of freedom. And for this case, we will have a new optical selection rule at k tau. This rule depends on the product of the spin and valley indices. When left polarized light sigma plus illuminates the sample, spin up electrons are excited to the conduction band at k plus, as well as the spin down electrons excited to conduction band of k minus. Yes. And vice versa for opposite polarization. In addition, in such a system, the k plus and k minus valleys have opposite Berry curvatures. Berry curvature is a difficult mathematical object, but we can understand it in this case as an effective magnetic field which induces very contrasting Hall currents. So, if we have opposite Berry curvatures for opposite k points, it means that we have circle dichroism Hall effect. This effect will consist in the fact that for left and right polarized lights, we will have opposite transversal conductivity, as shown in the figure. This effect is interesting because it makes possible conversion of optical polarization to electrical signal. Recently, this year, an article was published with a theoretical implementation of an antiferromagnetic ordering in the superatomic graphene. In this model, exchange term was much greater than the sublattice Hopring term. It means that this model represents so-called Dirac mode insulator. For this model, the electronic structure was calculated, and it was predicted the manifestation of circle dichroism Hall effect. However, it was just a theoretical model that had not been tested experimentally. Next, I would like to move on from the introduction to our own results and briefly stop on the experimental methods that we use. We study the electronic structure of a valence band by means of angle result photoelectron spectroscopy. This technique gives us information about the dispersion of valence electrons in the initial state. The atomic structure of two-dimensional system can be effectively studied by low electron energy diffraction, and some additional information about surface structure can be obtained by using some microscopic techniques. So, the system under study today represents a layered structure consisting of a cobalt crystal, a gold monolayer, and graphene layer on the surface. This heterostructure is interesting primarily because graphene in such a system is quasi-freestanding and retains its Dirac Coulomb. However, the proximity of graphene to metals with strong spin-orbit interaction and exchange coupling leads to the fact that the cone experiences noticeable exchange and spin-orbit splitting. And we called this structure magnetospin-orbit graphene. Diffraction data show that graphene in such a system forms a large superstructure with a size 10 by 10 with respect to graphene unit cell. Our microscopic data reveal the presence of periodical triangular defects in the system. The same defects have already been observed in the gold or nickel system, and were explained by the presence of dislocation loops. And we suppose that we have also a net of periodical dislocation loops in our system too. These dislocations are formed because of removing a row of 6 cobalt atoms from first cobalt layer while during the formation of a gold-cobalt alloy. Next, we created a theoretical model of a graphene gold-cobalt system containing periodical dislocation loops and performed structural optimizations with model by means of DFT calculations. After that, we conducted a simulation of STM images for our model and made sure that there is a good agreement between experimental pictures, STM images, and theoretical simulation. Also, we have found that the presence of loop dislocation leads to a ferromagnetic ordering of graphene along the cobalt z-axis of magnetization. It was very unexpected for us. And it is worth noting that in the absence of dislocations, we will get the usual ferromagnetic graphene. I would like to remind you that ferromagnetic ordering means that our system can potentially reveal the so-called dichroism Hall effects. In this slide, you can see the results of electronic structure calculations for our system for 2 opposite K points. As you can see, DFT predicts the appearance of band gap at K point and the exchange splitting of the cone states. It is caused by the hybridization with loop dislocation states. Also, calculations predict small spin-orbit splitting caused by the proximity of gold atoms. In the case of calculating the paramagnetic phase of our system, the band gap is closed, which indicates its obvious magnetic nature. The results of our calculations are converted by the experimental data. Here you can see RPS data for graphene Dirac cone. On this picture, you can see that experimental data also reveal a band gap in a Dirac point as well as in the calculations. Also required photoelectron spin result spectra for slices of RPS map K1, K2, and K3 with photoelectron spectra. And these data demonstrate that there is an exchange splitting of a magnitude like 1 in calculations. Also, you can notice that spin splitting has asymmetry for 2 opposite K points, and it is larger than in calculations. However, this is an expected fact because it is known that the DFT does not quite correctly estimate the graphene gold distance, and it leads to decrease in the spin-orbit coupling estimation in calculations. To better understand the band structure of ferromagnetic graphene, we reproduce Dirac cone states by a tie binding model for our system. Our model Hamiltonian contains 3 parts: sublattice hopping term, spin-orbit interaction, and exchange term. As a result, our model confirmed that ferromagnetism in graphene, in the presence of spin-orbit coupling contribution, should actually give the picture that we observe in the experiment and DFT calculations. Then we use our model to calculate the curvatures for Dirac cone states. As you can see, the curvatures are opposite for opposite K points. And as you can remember, it means that this system can reveal so-called dichroism Hall effect. So that concludes my presentation. Here you can see the brief conclusions of my work. I would like to just highlight that we propose a sublattice ferromagnetism of graphene in the graphene gold cobalt system, and suppose that the structure can be effectively applied in the electronics due to the presence of so-called dichroism Hall effect. This is exactly what I wanted to show you with my presentation, and I thank you for your attention.
Thank you very much, Artem. Are there any questions? Well, I can really, students or young scientists questions, don't be shy. Okay, can I ask you a simple question, because I'm not really in the topic, but you mentioned that the presence of loop dislocations in some cases can lead to ferromagnetic ordering. So what is the mechanism behind? I missed that, or maybe I missed the point here.
It is a big question. We are not sure how it happens. We just verify that the absence leads to ferromagnetic ordering in graphene. And only in the case of the presence of these dislocation loops, we can observe such unusual ferromagnetic ordering. And it is our object for further investigations. It's for big questions.
So you see that experimentally, but you don't have any explanation yet.
We cannot understand yet the mechanism. We're sure that it is ferromagnetism because we construct some simple model for ferromagnetic graphene, and we get the same band electronic structure as in DFT and the experiment. So we are sure about this the revealing of this phenomenon, but not sure about its nature.
Thank you, Artem. So yes, the next speaker is Alexander Pavlov with a talk entitled "Crystal Polarity Discrimination in Gallium Nitride Nanowires on Graphene."
Yes, thank you, Professor Dubrovsky, for kind introduction. Do you hear me? Do you see my screen?
Yes, everything seems to work.
Oh, so the title of my work was already said, and this work is done in collaboration with my colleagues from Alfyorov University and State University of St. Petersburg, and also a colleague from France. And as it was already said many times today, gallium nitride is a promising material for many optical electron and piezo applications, and this material can be grown in form of nanowires, which are main interest because of their unique properties. And what is actually polarity discrimination and what is polarity? And the first thing which one should know is that if the structure is grown in Wurtzerit crystalline structure, the absence of inversion point leads to two possible crystalline orientation. They're usually called N polarity and gallium polarity, and the difference between them is the orientation between gallium and nitrogen dipole. And it was experimentally shown that on graphene virtual substrate, the polarity of grown nanowires are primarily nitrogen. And it was done following. It is known that potassium hydroxide selectively etch only nitrogen polar surface of the nanowire of the crystal. And as you can see here on the left side, we have some image of nanowires grown on graphene substrate before potassium hydroxide attack and after attack. And as you can see here, the pencil-like top shapes actually indicate that the material was selectively etched, and we can see that almost all nanowires are n-polar, and that's actually really interesting because, for example, for pure silicon oxide, which is the substrate on which graphene was placed, we can see, for example, that both n-polar and gallium-polar crystal can grow. But if we add graphene, we see only n-polar crystals, nanowires. And we choose DFT, ab initio calculations, using DFT approach to analyze these experimental results. And we use 60 carbon atoms as a graphene monolayer, and we put on top of this graphene monolayer the small gallium nitride nanocrystal, which shape is the smallest possible crystal which can represent the symmetry of the system. And as you can see here, this system consists of 4 layers, and all possible configuration are depicted here. So we have 4 gallium polar nanocrystals, and we have 4 nitrogen polar nanocrystals. And if you look on the top figure, we can see that to -1 direction of cluster is along the zigzag direction of graphene substrate. After we construct all possible systems, we have done the energy optimization. So we try to optimize energy and minimize forces which are applied to the atoms in our calculation. Quick notice, we don't include in calculation in optimization graphene layer, so graphene layer is remain fixed because otherwise it will require much more time. So, and the results of the optimization procedure is quite interesting. We found out that 6 of 8 configurations were unstable during the optimization. And as you can see, for example, here we have 2 examples, one gallium polar and another nitrogen polar. And as you can see during the optimization procedure, so here we have some intermediate steps, and here we have optimized structure. We can see that nitrogen evaporates from the system. So evaporation here is in quotation mark, but nitrogen forms a molecule which is very energy efficient. And that means that these structures, these 6 of 8 structures, were so energetically unfavorable that they can really exist in real experiments. So we shouldn't consider them. But on the other hand, we find 2 stable configuration. First, gallium polar, and second, nitrogen polar. And for nitrogen polar, we can see that during the optimization, the nanocrystal slightly adjusts its shape, but nitrogen polarity and order of atomic layers remains the same. While for gallium power crystal, we find out that during the optimization, as you can see, the order of layers changes, and the gallium power nanocrystal becomes nitrogen power nanocrystal, which is very interesting, and we should somehow explain these results. And after some discussion, we consider dipole moment of such nanocrystal as a good microscopic physical quantity to explain the obtained results. And as one can notice, the total dipole moment of the nanocrystal can be explained as sum of atomic dipole moments, of contribution from atomic dipole moments, plus a contribution from partial charges, which just due to electron exchange between gallium and nitrogen. And as you can see here, for two possible nanocrystals, we have total system energy, which is just depends on the type of calculation, and dipole moment. And as you can see, even systems starts from different points in this figure. So dipole moment of gallium power nanocrystal is very high, and nitrogen power crystal have lesser dipole moment. But during the optimization, they all ends up in almost exact dipole moment and slightly different energy. It happens just because we can't proceed our optimization just until they find the global minimum. We just try to find some local minimum because every calculation is very expensive. And as you can see here, the main reason why our system prefers nitrogen polarity and this order of atoms, atom layers, is just because it is energetically favorable and it is stable when the system is stable when it has negative dipole moment. So n-polar crystal just initially have n-polar crystal initially has very small dipole moment, and during optimization it adjusts its shape and dipole moment also. But for gallium polar crystal, it should be noted that in order to achieve the desired stable configuration, the order of layers should be changed, and so we can see that for gallium polar nanocrystal, system changes much more than for nitrogen power. And after we find out that it is energetically favorable to have negative dipole moment, we remembered that for graphene sheet we have p orbitals, which are negative electron density above and below graphene sheet. So here you can see just a schematic representation of this dipole. So we have plus charge on graphene sheet, and below and above we have negative electron density. And as you can understand, these dipole moment interact with the dipole moment of the nanocrystal, and that is how to say, and that can be thought as a toy model to understand the nitrogen polarity of such systems. So we have done the calculation and show the results exactly. And now we just propose a simpler model to consider. So conclusions are the following. In this work, we demonstrated experimentally and theoretically, or computationally, the polarity discrimination of Gallium nanowires. DFT optimization shows that gallium polar nanocrystal adjusted shapes to n-polar nanocrystal, and for n-polar everything just already fine. And we introduce the projection of dipole moment as a good merit for explaining such systems, and we introduce a simple model which can be used as a simple explanation. I want to once again thank my colleagues and acknowledge some financial support. If anybody interested in this, the results in details can be found in following works. And thank you for your attention.
Thank you very much, Alexander. Are there any questions? So, how time-consuming are your DFT calculations, and which computer or which computers are used?
All calculations which are presented here, it was around 2 months, and we use both a small cluster in our lab and a supercomputer of Polytechnic University as a huge machine which can handle the calculation. So it's around months of computer.
You mean St. Petersburg Polytechnical University?
Yeah, St. Petersburg Polytechnic University. So,
any further questions? I don't see any questions, so let's thank the speaker again.
Thank you.
So the last talk of this session should be given by Nick Siberyov, but I don't see him because he was, I think he was sick. Nick, are you with us? Nick, Kolya, are you with us? He was sick yesterday, so probably we will wait for 1 minute just in case, but otherwise I will cancel the last talk. I don't see him among the participants all the day, so. So perhaps we should cancel the last talk, and therefore we can close the program for today. Thank you all for your attention and for your participation in the conference. I very much enjoyed the talks, particularly, I mean, of course, you can expect the best talks from the invited speakers, but the student talks I enjoyed very much as well. So that's all for today. If you don't have any questions to me. No questions. So so tomorrow we start at 9:45 using the same Zoom link, of course. Thank you very much, and bye-bye. Have a good evening.
Thank you. Goodbye, everybody.
Thank you.
Bye.